Chapter 6. Field effect transistors. Objectives. 1. Derive current voltage characteristics of junction field effect transistors, metal semiconductor field effect transistors, and HEMTs. 2. Determine metal oxide semiconductor current voltage behavior and threshold voltage, study leakage characteristics of gate dielectrics. 3. Understand metal oxide semiconductor field effect transistor band diagrams, and linear and saturation behavior. 4. Understand effective channel mobility, body effect, and subthreshold slopes. 5. Analyze second-order effects: drain-induced barrier lowering, gate-induced drain leakage, charge sharing, and threshold voltage roll-off. The modern era of semiconductor electronics was ushered in by the invention of the bipolar transistor in 1948 by Bardeen, Brattain, and Shockley at the Bell Telephone Laboratories. This device, along with its field effect counterpart, has had an enormous impact on virtually every area of modern life. In this chapter we will learn about the operation, applications, and fabrication of the field effect transistor, FET. The FET comes in several forms. In a junction field effect transistor, called a junction field effect transistor, the control gate voltage varies the depletion width of a reverse-biased p-n junction. A similar device results if the junction is replaced by a Schottky barrier, metal semiconductor FET, called a MES FET. Alternatively, the metal gate electrode may be separated from the semiconductor by an insulator, metal insulator semiconductor FET, called a MIS FET. A common special case of this type uses an oxide layer as the insulator, MOSFET. In Chapter 5 we found that two dominant features of p-n junctions are the injection of minority carriers with forward bias and a variation of the depletion width W with reverse bias. These two p-n junction properties are used in two important types of transistors. The bipolar junction transistor, BJT, discussed in Chapter 7 uses the injection of minority carriers across a forward-biased junction, and the GFET discussed in this chapter depends on control of a junction depletion width under reverse bias. The FET is a majority carrier device, and is therefore often called a unipolar transistor. The BJT, on the other hand, operates by the injection and collection of minority carriers. Since the action of both electrons and holes is important in this device, it is called a bipolar transistor. Like its bipolar counterpart, the FET is a three-terminal device in which the current through two terminals is controlled at the third. Unlike the BJT, however, field effect devices are controlled by a voltage at the third terminal rather than by a current. The history of BJTs and FETs is rather interesting. It was the FET that was proposed first in 1930 by Lilienfeld, but he never got it to work because he did not fully appreciate the role of surface defects or surface states. In the process of trying to demonstrate experimentally such a FET, Bardeen and Brattain somewhat serendipitously invented the first bipolar transistor, the germanium point contact transistor. This major breakthrough was rapidly followed by Shockley's extension of the concept to the BJT. It was only much later, after the problem of surface states was resolved by growing an oxide insulator on silicon, that the first MOSFET was demonstrated in 1960 by Kong and Atala. Although the BJT reigned supreme in the early days of semiconductor integrated electronics, it has been gradually supplanted in most applications by the silicon MOSFET. The main reason is, unlike BJTs, the various types of FET are characterized by a high input impedance, since the control voltage is applied to a reverse-biased junction or Schottky barrier, or across an insulator. These devices are particularly well suited for controlled switching between a conducting state and a non-conducting state, and are therefore useful in digital circuits. They are also suitable for integration of many devices on a single chip, as we shall see in Chapter 9. In fact, billions of MOS transistors are commonly used together in semiconductor memory devices and microprocessors. We begin this section with a general discussion of amplification and switching, the basic circuit functions performed by transistors. The transistor is a three-terminal device with the important feature that the current through two terminals can be controlled by small changes we make in the current or voltage at the third terminal. This control feature allows us to amplify small AC signals or to switch the device from an on state to an off state and back. These two operations, amplification and switching, are the basis of a host of electronic functions. This section provides a brief introduction to these operations, as a foundation for understanding both bipolar and field effect transistors. The load line. Consider a two-terminal device, Fig 6, 1a, that has a nonlinear current voltage characteristic, as in Fig 6 1b. We might determine this curve experimentally by measuring the current for various applied voltages. When such a device is biased with the simple battery resistor combination shown in the figure, steady-state values of drain current and drain voltage are attained. To find these values we begin by writing a loop equation around the circuit. E = I*R plus V. Figure 6.1. A two-terminal nonlinear device. A. Biasing circuit. B. Current voltage characteristics and load line. This gives us one equation describing the circuit, but it contains two unknowns, drain current and drain voltage. Fortunately, we have another equation of the form ID = F, Vd, in the curve of Fig 6 1b, giving us two equations with two unknowns. The steady-state current and voltage are found by a simultaneous solution of these two equations. However, since one equation is analytical and the other is graphical, we must first put them into the same form. It is easy to make the linear equation, 6.1, graphical, so we plot it on Fig 6 1b to find the simultaneous solution. The endpoints of the line described by EQ 6.1 are at E when ID = 0 and at ER when VD = 0. The two graphs cross at VD = VD and ID = ID, the steady-state values of current and voltage for the device with this biasing circuit. Now let's add a third terminal which somehow controls the IV characteristic of the device, Fig 6, 2a. For example, assume that the device current voltage curve can be moved up the current axis by increasing the control voltage as in Fig 6 2b. This results in a family of drain current, drain voltage curves, depending upon the choice of gate voltage. We can still write the loop equation, 6.1, and draw it on the set of curves, but now the simultaneous solution depends on the value of gate voltage. In the example of Fig 6.2, gate voltage is 0.5 volts and the DC values of ID and VD are found at the intersection to be 10 mA and 5 volts, respectively. Whatever the value of the control voltage Vg at the third terminal, values of ID and VD are obtained from points along the line representing EQ. 6.1. This is called the load line. Amplification and switching. If an AC source is added to the control voltage, we can achieve large variations in drain current by making small changes in gate voltage. For example, as gate voltage varies about its DC value by 0.25 V in Fig 6.2, drain voltage varies about its DC value Vd by 2 volts. Thus the amplification of the AC signal is 2/0.25 = 8. If the curves for equal changes in gate voltage are equally spaced on the drain current axis, a faithful amplified version of the small control signal can be obtained. This type of voltage-controlled amplification is typical of field effect transistors. For bipolar transistors, a small control current is used to achieve large changes in the device current, achieving current amplification. Another important circuit function of transistors is the controlled switching of the device off and on. In the example of Fig 6.2, we can switch from the bottom of the load line, ID = 0, to almost the top, IDER, by appropriate changes in gate voltage. This type of switching with control at a third terminal is particularly useful in digital circuits. Figure 6.2. A three-terminal device that can be controlled by the voltage at terminal Vg, A, a biasing circuit, B, current voltage characteristics and load line. If Vg = 0.5 V, the direct current values are shown by the dashed lines. In a junction FET, GFET, the voltage variable depletion region width of a junction is used to control the effective cross-sectional area of a conducting channel. In the device of Fig 6.3, the current flows through an N-type channel between two P+ regions. A reverse bias between these P+ regions and the channel causes the depletion regions to intrude into the N material, and therefore the effective width of the channel can be restricted. Since the resistivity of the channel region is fixed by its doping, the channel resistance varies with changes in the effective cross-sectional area. By analogy, the variable depletion regions serve as the two doors of a gate, which open and close on the conducting channel. In Fig 6.3, electrons in the N-type channel drift from left to right, opposite to current flow. The end of the channel from which electrons flow is called the source, and the end toward which they flow is called the drain. The P+ regions are called gates. If the channel were P-type, holes would flow from the source to the drain, in the same direction as the current flow, and the gate regions would be N+. Figure 6.3. Simplified cross-sectional view of a junction field effect transistor. A. Transistor geometry. B. Detail of the channel and voltage variations along the channel with gate voltage equal to 0 and small drain current. It is common practice to connect the two gate regions electrically, therefore, the voltage gate voltage refers to the potential from each gate region gate to the source S. Since the conductivity of the heavily doped P+ regions is high, we can assume that the potential is uniform throughout each gate. In the lightly doped channel material, however, the potential varies with position, Fig 6.3b. If the channel of Fig 6.3 is considered as a distributed resistor carrying a current ID, it is clear that the voltage from the drain end of the channel drain to the source electrode S must be greater than the voltage from a point near the source end to S. For low values of current, we can assume a linear variation of voltage Vx in the channel, varying from Vd at the drain end to 0 at the source end, Fig 6.3b. Pinch off and saturation. In Fig 6.4 we consider the channel in a simplified way by neglecting voltage drops between the source and drain electrodes and the respective ends of the channel. For example, we assume that the potential at the drain end of the channel is the same as the potential at the electrode D. This is a good approximation if the source and drain regions are relatively large, so that there is little resistance between the ends of the channel and the electrodes. In Fig 6.4 the gates are short-circuited to the source, gate voltage equals 0, such that the potential at X equals 0 is the same as the potential everywhere in the gate regions. For very small currents, the widths of the depletion regions are close to the equilibrium values, Fig 6.4a. Figure 6.4. Depletion regions in the channel of a junction field effect transistor with zero gate bias for several values of drain voltage, A. Linear range, B. Near pinch off, C. Beyond pinch off. As the current drain current is increased, however, it becomes important that Vx is large near the drain end and small near the source end of the channel. Since the reverse bias across each point in the gate-to-channel junction is simply Vx when gate voltage is 0, we can estimate the shape of the depletion regions as in Fig 6.4b. The reverse bias is relatively large near the drain, gate drain voltage equal negative drain voltage, and decreases toward 0 near the source. As a result, the depletion region intrudes into the channel near the drain, and the effective channel area is constricted. Since the resistance of the constricted channel is higher, the current voltage plot for the channel begins to depart from the straight line that was valid at low current levels. As the voltage drain voltage and current drain current are increased still further, the channel region near the drain becomes more constricted by the depletion regions and the channel resistance continues to increase. As drain voltage is increased, there must be some bias voltage at which the depletion regions meet near the drain and essentially pinch off the channel, Fig 6.4c. When this happens, the drain current cannot increase significantly with further increase in drain voltage. Beyond pinch off the current is saturated approximately at its value at pinch off 2. Once electrons from the channel enter the electric field of the depletion region, they are swept through and ultimately flow to the positive drain contact. After the current saturates beyond pinch off, the differential channel resistance drain voltage divided by drain current becomes very high. To a good approximation, we can calculate the current at the critical pinch-off voltage and assume there is no further increase in current as drain voltage is increased. Figure 6.5. Effects of negative gate bias A, increase of depletion region widths with negative gate voltage B, family of current voltage curves for the channels as gate voltage is varied. Gate control. The effect of a negative gate bias, Vg, is to increase the resistance of the channel and induce pinch-off at a lower value of current, Fig 6.5. Since the depletion regions are larger with Vg negative, the effective channel width is smaller and its resistance is higher in the low current range of the characteristic. Therefore, the slopes of the ID versus Vd curves below pinch-off become smaller as the gate voltage is made more negative, Fig 6.5b. The pinch-off condition is reached at a lower drain-to-source voltage, and the saturation current is lower than for the case of zero gate bias. As gate voltage is varied, a family of curves is obtained for the current voltage characteristic of the channel, as in Fig 6.5b. Beyond the pinch-off voltage the drain current ID is controlled by gate voltage. By varying the gate bias we can obtain amplification of an AC signal. Since the input control voltage Vg appears across the reverse-biased gate junctions, the input impedance of the device is high. We can calculate the pinch-off voltage rather simply by representing the channel in the approximate form of Fig 6.6. If the channel is symmetrical and the effects of the gates are the same in each half of the channel region, we can restrict our attention to the channel half width h, x, measured from the center line, y equals 0. The metallurgical half-width of the channel, i.e., neglecting the depletion region, is A. We can find the pinch-off voltage by calculating the reverse bias between the N channel and the P plus gate at the drain end of the channel, X equal L. For simplicity we shall assume that the channel width at the drain decreases uniformly as the reverse bias increases to pinch-off. Figure 6.6. Simplified diagram of the channel with definitions of dimensions and differential volume for calculations. If the reverse bias between the gate and the drain is VGD, the width of the depletion region at X equal L can be found from EQ 557. In this expression we assume the equilibrium contact potential V0 is negligible compared with VGD and the depletion region extends primarily into the channel for the P plus, N junction. Including V0 is left for Prob 6.1. Pinch-off occurs at the drain end of the channel when, that is, when W, X equal L, equal A. If we define the value of VGD at pinch-off as Vp, we have the pinch-off voltage Vp is a positive number, its relation to drain voltage and gate voltage is where Vg is 0 or negative for proper device operation. A forward bias on the gate would cause hole injection from the P plus regions into the channel, eliminating the field effect control of the device. From EQ 6.5, it is clear that pinch-off results from a combination of gate-to-source voltage and drain-to-source voltage. Pinch-off is reached at a lower value of Vd, and therefore a lower ID, when a negative gate bias is applied, in agreement with Fig 6.5b. Current voltage characteristics. Calculation of the exact channel current is complicated, although the mathematics is relatively straightforward below pinch-off. The approach we shall take is to find the expression for ID just at pinch-off, and then assume the saturation current beyond pinch-off remains fairly constant at this value. In the coordinate system defined in Fig 6.6, the center of the channel at the source end is taken as the origin. The length of the channel in the x direction is L, and the depth of channel in the z direction is Z. We shall call the resistivity of the n-type channel material T, valid only in the neutral N material, outside the depletion regions. If we consider the differential volume of neutral channel material Z2H, X, dx, the resistance of the volume element is T dx Z2H, X, CEQ 344. Since the current does not change with distance along the channel, ID is related to the differential voltage change in the element dV. x by the conductance of the element. The term 2h, x, is the channel width at x. The half width of the channel at point x depends on the local reverse bias between gate and channel, VGX. Since VGX equal VG, Vx and Vp equal QA2n/2p. Implicit in EQ 6.7 is the assumption that the expression for W, x, can be obtained by a simple extension of EQ 6.2 to point x in the channel. This is called the gradual channel approximation. It is valid if h, x, does not vary abruptly in any element dx. The voltage VGX will be negative since the gate voltage VG is chosen 0 or negative for proper operation. Substituting EQ 6.7 into EQ 6.6. We can solve this equation to obtain where Vg is negative and G0K2AZTL is the conductance of the channel for negligible W, x, that is, with no gate voltage and low values of ID. This equation is valid only up to pinch off, where VdVg equal Vp. If we assume the saturation current remains essentially constant at its value at pinch off, we have where the resulting family of current voltage curves for the channel agrees with the results we predicted qualitatively, Fig 6.5b. The saturation current is greatest when Vg is 0 and becomes smaller as Vg is made negative. We can represent the device biased in the saturation region by an equivalent circuit where changes in drain current are related to gate voltage changes by the quantity Gm is the mutual transconductance, with units, A/V, called Siemens, S, sometimes called mhos. As a figure of merit for FET devices, it is common to describe the transconductance per unit channel width Z. This quantity GmZ is usually given in units of millisiemens per millimeter. It is found experimentally that a square law characteristic closely approximates the drain current in saturation, where IDSS is the saturated drain current with Vg equals 0. The appearance of a constant value of channel resistivity, in the G0 term, in EQs 6.9, 6.11, implies that the electron mobility is constant. As mentioned in section 3.4.4, electron velocity saturation at high fields may make this assumption invalid. This is particularly likely for very short channels, where even moderate drain voltage can result in a high field along the channel. Another departure from the ideal model results from the fact that the effective channel length decreases as the drain voltage is increased beyond pinch-off, as Fig 6.4c suggests. In short channel devices, this effect can cause drain current to increase beyond pinch-off, since L appears in the denominator of EQ 6.10, in G0. Therefore, the assumption of constant saturation current is not valid for very short channel devices. The depletion of the channel discussed above for a GFET can be accomplished by the use of a reverse-biased Schottky barrier instead of a PN junction. The resulting device is called a MESFET, indicating that a metal semiconductor junction is used. This device is useful in high-speed digital or microwave circuits, where the simplicity of Schottky barriers allows fabrication to close geometrical tolerances. There are particular speed advantages for MESFET devices in IIIV compounds such as gallium arsenide or indium phosphide, which have higher mobilities and carrier drift velocities than silicon. The gallium arsenide MESFET. Figure 6.7 shows schematically a simple MESFET in gallium arsenide. The substrate is undoped or doped with chromium, which has an energy level near the center of the gallium arsenide band gap. In either case, the Fermi level is near the center of the gap, resulting in very high resistivity material 100 megaohms per centimeter, generally called semi-insulating gallium arsenide. On this non-conducting substrate, a thin layer of lightly doped N-type gallium arsenide is grown epitaxially, to form the channel region of the FET3. The photolithographic processing consists of defining patterns in the metal layers for source and drain ohmic contacts, for example, gold germanium, and for the Schottky barrier gate, for example, aluminum. By reverse biasing the Schottky gate, the channel can be depleted to the semi-insulating substrate, and the resulting current voltage characteristics are similar to the GFET device. By using gallium arsenide instead of silicon, a higher electron mobility is available, see Appendix 3, and furthermore gallium arsenide can be operated at higher temperatures, and therefore higher power levels. Since no diffusions are involved in Fig 6-7, closed geometrical tolerances can be achieved and the MESFET can be made very small. Gate lengths LF50 nanometers are common in these devices. This is important at high frequencies, since drift time and capacitances must be kept to a minimum. It is possible to avoid the epitaxial growth of the N-type layer and the etched isolation in Fig 6-7 by using ion implantation. Starting with a semi-insulating gallium arsenide substrate, a thin N-type layer at the surface of each transistor region can be formed by implanting silicon or a column 6 donor impurity such as selenium. Figure 6-7. Gallium arsenide metal semiconductor field effect transistor formed on an N-type gallium arsenide layer grown epitaxially on a semi-insulating substrate. Common metals for the Schottky gate in gallium arsenide are aluminum or alloys of titanium, wolfram, and gold. The ohmic source and drain contacts may be an alloy of gold and germanium. In this example, the device is isolated from others on the same chip by etching through the N region to the semi-insulating substrate. This implantation requires an anneal to remove the radiation damage, but the epitaxial growth step is eliminated. In either the fully implanted device or the epitaxial device of Fig 6-7, the source and drain contacts may be improved by further N+ implantation in these regions. Because of the relative simplicity of implanted gallium arsenide MESFETs and the isolation between devices provided by the semi-insulating substrate, these structures are commonly used in gallium arsenide integrated circuits. The high electron mobility transistor, HEMT. Since the metal semiconductor field effect transistor, MESFET, is compatible with the use of 3,5 compounds, it is possible to exploit the band gap engineering available with heterojunctions in these materials. In order to maintain high transconductance in a MESFET, the channel conductivity must be as high as possible. Obviously, the conductivity can be increased by increasing the doping in the channel and thus the carrier concentration. However, increased doping also causes increased scattering by the ionized impurities, which leads to a degradation of mobility, see Fig 323. What is needed is a way of creating a high electron concentration in the channel of a MESFET by some means other than doping. A clever approach to this requirement is to grow a thin undoped well, for example, gallium arsenide, bounded by wider band gap, doped barriers, for example, aluminum gallium arsenide. This configuration, called modulation doping, results in conductive gallium arsenide when electrons from the doped aluminum gallium arsenide barriers fall into the well and become trapped there, as shown in Fig 6-8a. Since the donors are in the aluminum gallium arsenide rather than the gallium arsenide, there is no impurity scattering of electrons in the well. If a MESFET is constructed with the channel along the gallium arsenide well, perpendicular to the page in Fig 6-8, we can take advantage of this reduced scattering and resulting higher mobility. The effect is especially strong at low temperature where lattice, phonon, scattering is also low. This device is called a modulation doped field effect transistor, MODFET, and is also called a high electron mobility transistor, HEMT. Figure 6-8a, simplified view of modulation doping, showing only the conduction band. Electrons in the donor-doped aluminum gallium arsenide fall into the gallium arsenide potential well and become trapped. As a result, the undoped gallium arsenide becomes N-type, without the scattering by ionized donors which is typical of bulk N-type material. B. Use of a single aluminum gallium arsenide/gallium arsenide heterojunction to trap electrons in the undoped gallium arsenide. The thin sheet of charge due to free electrons at the interface forms a two-dimensional electron gas, which can be exploited in high electron mobility transistor devices. In Fig 6.8a we have left out the band bending expected at the aluminum gallium arsenide/gallium arsenide interfaces. Based upon the discussion in section 5.8, we expect the electrons to accumulate at the corners of the well due to band bending at the heterojunction. In fact, only one heterojunction is required to trap electrons, as shown in Fig 6.8b. Generally, the donors in the aluminum gallium arsenide layer are purposely separated from the interface by 100 angstroms. Using this configuration, we can achieve a high electron concentration in the channel while retaining high mobility, since the gallium arsenide channel region is spatially separated from the ionized impurities which provide the free carriers. In Fig 6.8b, mobile electrons generated by the donors in the aluminum gallium arsenide diffuse into the small bandgap gallium arsenide layer, and they are prevented from returning to the aluminum gallium arsenide by the potential barrier at the aluminum gallium arsenide/gallium arsenide interface. The electrons in the, almost, triangular well form a two-dimensional electron gas, sometimes abbreviated to, DEG. Sheet carrier densities as high as 10-12 cm, 2 can be obtained at a single interface such as that shown in Fig 6.8b. Ionized impurity scattering is greatly reduced simply by separating the electrons from the donors. Also, screening effects due to the extremely high density of the two-dimensional electron gas can reduce ionized impurity scattering further. In properly designed structures, the electron transport approaches that of bulk gallium arsenide with no impurities, so that mobility is limited by lattice scattering. As a result, mobilities above 250,000 square centimeters per volt at 77 kelvins and 2 million square centimeters per volt at 4 kelvins can be achieved. The advantages of a high electron mobility transistor are its ability to locate a large electron density, trillion electrons per square centimeter, in a very thin layer, 100 angstroms thick, very close to the gate while simultaneously eliminating ionized impurity scattering. The aluminum gallium arsenide layer in a high electron mobility transistor is fully depleted under normal operating conditions, and since the electrons are confined to the heterojunction, device behavior closely resembles that of a MOSFET. The advantages of the high electron mobility transistor over the silicon MOSFET are the higher mobility and maximum electron velocity in GaAs compared with silicon, and the smoother interfaces possible with an aluminum gallium arsenide/gallium arsenide heterojunction compared with the silicon/silicon dioxide interface. The high performance of the HEMT translates into an extremely high cutoff frequency, and devices with fast access times. Although we have discussed the high electron mobility transistor in terms of the aluminum gallium arsenide/gallium arsenide heterojunction, other materials are also promising, such as the indium gallium arsenide phosphide/indium phosphide system. A motivation for avoiding aluminum X gallium 1, X arsenide is the presence of a deep level defect called the DX center for X70.2, which traps electrons and impairs the high electron mobility transistor operation. Since very thin layers are involved, materials with slight lattice mismatch can be grown to form pseudomorphic HEMTs. An example of such a system is the use of a thin layer of indium gallium arsenide grown pseudomorphically on gallium arsenide, followed by aluminum gallium arsenide. An advantage of this system is that a useful band discontinuity can be achieved using aluminum gallium arsenide of low enough aluminum composition to avoid the DX center problem. The high electron mobility transistor, or MODFET, is also referred to as a two-dimensional electron gas field effect transistor, 2, DEGFET, or TEGFET, to emphasize the fact that conduction along the channel occurs in a thin sheet of charge. The device has also been called a separately doped FET, SEDFET, to emphasize the fact that the doping occurs in a separate region from the channel. Short channel effects. As mentioned in section 6.2.3, a variety of modifications to the simple theory of GFET and MESFET operation must be made when the channel length is small, typically less than 1 micrometer. In the past, these short channel effects would be considered unusual, but now it is common to encounter FET devices in which these effects dominate the current voltage characteristics. For example, high field effects occur when 1 volt appears across a channel length of 1 micrometer, 1 millionth part of meter, giving an electric field of 10 kilovolts per centimeter. A simple piecewise linear approximation to the velocity field curve assumes a constant mobility, linear, dependence up to some critical field C and a constant saturation velocity versus for higher fields. For silicon a better approximation is where O is the low field mobility. These two approximations are shown in Fig 6.9a. If we assume that the electrons passing through the channel drift with a constant saturation velocity v, the current takes a simple form, where h is a slow function of gate voltage. In this case the saturated current follows the velocity saturation, and does not require a true pinch-off in the sense of depletion regions meeting at some point in the channel. In the saturated velocity case, the transconductance Gm is essentially constant, in contrast with the constant mobility case described by EQ. 6.11. As shown in Fig 6.9b, the drain current, drain voltage curves are more evenly spaced if constant saturation velocity dominates, compared with the gate voltage dependent spacing shown in Fig 6.5b for the long channel constant mobility case. Most devices operate with characteristics intermediate between the constant mobility and the constant velocity regimes. Depending on the details of the field distribution, it is possible to divide up the channel into regions dominated by the two extreme cases, or to use an approximation such as EQ. 6.13. Another important short channel effect, described in section 6.2.3, is the reduction in effective channel length after pinch-off as the drain voltage is increased. This effect is not significant in long channel devices, since the change in L due to intrusion of the depletion region is a minor fraction of the total channel length. In short channel devices, however, the effective channel length can be substantially shortened, leading to a slope in the saturated current voltage characteristic that is analogous to the early, base width narrowing, effect in bipolar transistors discussed in section 7.7.2. Figure 6.9. Effects of electron velocity saturation at high electric fields. A. Approximations to the saturation of drift velocity with increasing field. B. Drain current voltage characteristics for the saturated velocity case, showing almost equally spaced curves with increasing gate voltage. One of the most widely used electronic devices, particularly in digital integrated circuits, is the metal insulator semiconductor, MIS, transistor. In this device the channel current is controlled by a voltage applied at a gate electrode that is isolated from the channel by an insulator. The resulting device may be referred to generically as an insulated gate field effect transistor, IGFET. However, since most such devices are made using silicon for the semiconductor, silicon dioxide or other oxides for the insulator, and metal or heavily doped polysilicon for the gate electrode, the term MOS field effect transistor, MOSFET, is commonly used. Basic operation and fabrication. The basic MOS transistor is illustrated in Fig 6.10a for the case of an enhancement mode N-channel device formed on a P-type silicon substrate. The N+ source and drain regions are diffused or implanted into a relatively lightly doped P-type substrate, and a thin oxide layer separates the conducting gate from the silicon surface. No current flows from drain to source without a conducting N-channel between them. This can be understood clearly by looking at the band diagram of the MOSFET in equilibrium along the channel, Fig 6.10a. The Fermi level is flat in equilibrium. The conduction band is close to the Fermi level in the N+ source/drain, while the valence band is closer to the Fermi level in the P-type material. Hence, there is a potential barrier for an electron to go from the source to the drain, corresponding to the built-in potential of the back-to-back p-n junctions between the source and drain. Figure 6-10. An enhancement type N-channel MOSFET. A. Isometric view of device equilibrium band diagram along channel. B. Drain current, voltage output characteristics as a function of gate voltage. When a positive voltage is applied to the gate relative to the substrate, which is connected to the source in this case, positive charges are in effect deposited on the gate metal. In response, negative charges are induced in the underlying silicon, by the formation of a depletion region and a thin surface region containing mobile electrons. These induced electrons form the channel of the FET, and allow current to flow from drain to source. As Fig 610b suggests, the effect of the gate voltage is to vary the conductance of this induced channel for low drain to source voltage, analogous to the GFET case. Since electrons are electrostatically induced in the p-type channel region, the channel becomes less p-type, and therefore the valence band moves down, farther away from the Fermi level. This obviously reduces the barrier for electrons between the source, the channel, and the drain. If the barrier is reduced sufficiently by applying a gate voltage in excess of what is known as the threshold voltage, Vt, there is significant current flow from the source to the drain. Thus, one view of a MOSFET is that it is a gate-controlled potential barrier. It is very important to have high-quality, low-leakage p-n junctions in order to ensure a low off-state leakage in the MOSFET. For a given value of Vg there will be some drain voltage Vd for which the current becomes saturated, after which it remains essentially constant. The threshold voltage Vt is the minimum gate voltage required to induce the channel. In general, the positive gate voltage of an n-channel device, such as that shown in Fig 611, must be larger than some value Vt before a conducting channel is induced. Similarly, a p-channel device, made on an n-type substrate with p-type source and drain implants or diffusions, requires a gate voltage more negative than some threshold value to induce the required positive charge, mobile holes, in the channel. There are exceptions to this general rule, however, as we shall see. For example, some n-channel devices have a channel already with zero gate voltage, and in fact a negative gate voltage is required to turn the device off. Such a normally on device is called a depletion mode transistor, since gate voltage is used to deplete a channel which exists at equilibrium. The more common MOS transistor is normally off with zero gate voltage, and operates in the enhancement mode by applying gate voltage large enough to induce a conducting channel. An alternative view of a MOSFET is that it is a gate-controlled resistor. If the positive gate voltage exceeds the threshold voltage in an n-channel device, electrons are induced in the p-type substrate. Since this channel is connected to the n+ source and drain regions, the structure looks electrically like an induced n-type resistor. As the gate voltage increases, more electron charge is induced in the channel and, therefore, the channel becomes more conducting. The drain current initially increases linearly with the drain bias, the linear regime, Fig 610b. As more drain current flows in the channel, however, there is more ohmic voltage drop along the channel such that the channel potential varies from zero near the grounded source to whatever the applied drain potential is near the drain end of the channel. Hence, the voltage difference between the gate and the channel reduces from Vg near the source to Vg, Vd, near the drain end. Once the drain bias is increased to the point that Vg, Vd, equal Vt, threshold is barely maintained near the drain end, and the channel is said to be pinched off. Increasing the drain bias beyond this point, Vd, SAD, causes the point at which the channel gets pinched off to move more and more into the channel, closer to the source end, Fig 611c. Electrons in the channel are pulled into the pinch-off region and travel at the saturation drift velocity because of the very high longitudinal electric field along the channel. Now, the drain current is said to be in the saturation region because it does not increase with drain bias significantly, Fig 610b. Actually, there is a slight increase of drain current with drain bias due to various effects such as channel length modulation and drain-induced barrier lowering, DIBL, that will be discussed in section 6.5.10 figure 6 to 11. N-channel metal oxide semiconductor field effect transistor cross-section under different operating conditions. A. Linear region for gate voltage greater than trace-hold voltage, and drain voltage smaller than difference between gate voltage and threshold voltage. B. Onset of saturation at pinch-off, gate voltage greater than threshold voltage, and drain voltage equal to difference between gate voltage and threshold voltage. C. Strong saturation, gate voltage greater than threshold voltage and drain voltage greater than difference between gate voltage and threshold voltage. The MOS transistor is particularly useful in digital circuits, in which it is switched from the off state, no conducting channel, to the on state. The control of drain current is obtained at a gate electrode which is insulated from the source and drain by the oxide. Thus the DC input impedance of an MOS circuit can be very large. Both N-channel and P-channel MOS transistors are in common usage. The N-channel type illustrated in Fig 610 is generally preferred because it takes advantage of the fact that the electron mobility in silicon is larger than the mobility of holes. In much of the discussion to follow we will use the N-channel, P-type substrate, example, although the P-channel case will be kept in mind also. Let us give a very simplified description of how such an N-channel MOSFET can be fabricated. A much more detailed discussion is given in section 9.3.1. An ultra-thin, few angstroms, dry thermal silicon dioxide is grown on the P-type substrate, followed by deposition of a so-called high-K dielectric such as hafnium dioxide. This serves as the gate insulator between the conducting gate and the channel. We cover it with a metal electrode which is then patterned to form the gates, and etched anisotropically by reactive ion etching, RE, to achieve vertical walls, section 5.1.7. The gate itself is used as an implant mask for an N+ implant which forms the source/drain junctions abutted to the gate edges, but is blocked from the channel region. Such a scheme is called a self-aligned process because we did not have to use a separate lithography step for the source/drain formation. Self-alignment is simple and is very useful because we thereby guarantee that there will be some overlap of the gate with the source/drain but not too much overlap. The advantages of this are discussed in section 6.5.8. The implanted dopants must be annealed for reasons discussed in section 5.1.4. Finally, the MOSFETs have to be properly interconnected according to the circuit layout, using metallization. This involves LPCVD of an oxide dielectric, etching contact holes by depositing a suitable metal such as copper, patterning and etching it. As shown in Fig 610a, the MOSFET is surrounded on all sides by a thick silicon dioxide layer. This layer provides critical electrical isolation between adjacent transistors on an integrated circuit. We shall see in section 9.3.1 that such isolation or field regions can be formed by shallow trench isolation, STI. Shallow grooves or trenches are etched in the substrate using and a thermal oxide is grown to passivate the surface and fill up the trench with LPCVD of silicon dioxide. The reason why a thick field oxide layer leads to electrical isolation is discussed in section 6.5.5. The ideal MOS capacitor. The surface effects that arise in an apparently simple MOS structure are actually quite complicated. Although many of these effects are beyond the scope of this discussion, we will be able to identify those which control typical MOS transistor operation. We begin by considering an uncomplicated idealized case, and then include effects encountered in real surfaces in the next section. Some important definitions are made in the energy band diagram of Fig 612a. The work function characteristic of the metal, see section 2.2.1, can be defined in terms of the energy required to move an electron from the Fermi level to outside the metal. In MOS work it is more convenient to use a modified work function Qm for the metal oxide interface. The energy QFM is measured from the metal Fermi level to the conduction band of the oxide. For similarly, QFS is the modified work function at the semiconductor oxide interface. In this idealized case we assume that Fm equal Fs, so there is no difference in the two work functions. Another quantity that will be useful in later discussions is QFF, which measures the position of the Fermi level below the intrinsic level EI for the semiconductor. This quantity indicates how strongly p-type the semiconductor is CEQ. 325. The MOS structure of Fig 612 is essentially a capacitor in which one plate is a semiconductor. If we apply a negative voltage between the metal and the semiconductor, Fig 612b, we effectively deposit a negative charge on the metal. In response, we expect an equal net positive charge to accumulate at the surface of the semiconductor. In the case of a p-type substrate, this occurs by hole accumulation at the semiconductor oxide interface. Since the applied negative voltage depresses the electrostatic potential of the metal relative to the semiconductor, the electron energies are raised in the metal relative to the semiconductor 5. As a result, the Fermi level for the metal EFM lies above its equilibrium position by QV, where V is the applied voltage. Since FM and Fs do not change with applied voltage, moving EFM up in energy relative to EFS causes a tilt in the oxide conduction band. We expect such a tilt since an electric field causes a gradient in EI, and similarly in EV and EC, as described in section 4.4.2. The energy bands of the semiconductor bend near the interface to accommodate the accumulation of holes. Since it is clear that an increase in hole concentration implies an increase in EIF at the semiconductor surface. Since no current passes through the MOS structure, there can be no variation in the Fermi level within the semiconductor. Therefore, if EIF is to increase, it must occur by EI moving up in energy near the surface. The result is a bending of the semiconductor bands near the interface. We notice in Fig 612b that the Fermi level near the interface lies closer to the valence band, indicating a larger hole concentration than that arising from the doping of the p-type semiconductor. Figure 612. Band diagram for the ideal metal oxide semiconductor structure at A, equilibrium, B, negative voltage causes hole accumulation in the p-type semiconductor, C, positive voltage depletes holes from the semiconductor surface, D, a larger positive voltage causes inversion and N-type layer at the semiconductor surface. In Fig 612c we apply a positive voltage from the metal to the semiconductor. This raises the potential of the metal, lowering the metal Fermi level by QV relative to its equilibrium position. As a result, the oxide conduction band is again tilted. We notice that the slope of this band, obtained by simply moving the metal side down relative to the semiconductor side, is in the proper direction for the applied field, according to EQ. 426. The positive voltage deposits positive charge on the metal and calls for a corresponding net negative charge at the surface of the semiconductor. Such a negative charge in p-type material arises from depletion of holes from the region near the surface, leaving behind uncompensated ionized acceptors. This is analogous to the depletion region at a p-n junction discussed in section 5.2.3. In the depleted region the hole concentration decreases, moving EI closer to F, and bending the bands down near the semiconductor surface. If we continue to increase the positive voltage, the bands at the semiconductor surface bend down more strongly. In fact, a sufficiently large voltage can bend EI below F, Fig 612d. This is a particularly interesting case, since FEI implies a large electron concentration in the conduction band. The region near the semiconductor surface in this case has conduction properties typical of N-type material, with an electron concentration given by EQ. 325a. This N-type surface layer is formed not by doping, but instead by inversion of the originally p-type semiconductor due to the applied voltage. This inverted layer, separated from the underlying p-type material by a depletion region, is the key to most transistor operation. We should take a closer look at the inversion region, since it becomes the conducting channel in the FET. In Fig 613 we define a potential H at any point x, measured relative to the equilibrium position of EI. The energy QH tells us the extent of band bending at x, and QHS represents the band bending at the surface. We notice that HS equals 0 is the flat band condition for this ideal MOS case, i.e., the bands look like Fig 612a. When HS 60, the bands bend up at the surface, and we have hole accumulation, Fig 612b. Similarly, when HS 70, we have depletion, Fig 612c. Finally, when HS is positive and larger than HF, the bands at the surface are bent down such that EI, x equals 0, lies below F, and inversion is obtained, Fig 612d. While it is true that the surface is inverted whenever Hs is larger than Ff, a practical criterion is needed to tell us whether a true n-type conducting channel exists at the surface. The best criterion for strong inversion is that the surface should be as strongly n-type as the substrate is p-type. That is, EI should lie as far below F at the surface as it is above F far from the surface. This condition occurs when a surface potential of HF is required to bend the bands down to the intrinsic condition at the surface, EI equal F, and EI must then be depressed another QHF at the surface to obtain the condition we call strong inversion. Figure 6.13. Bending of the semiconductor bands at the onset of strong inversion. The surface potential Fs is twice the value of Ff in the neutral p material. The electron and hole concentrations are related to the potential H, X, defined in Fig 6.13. Figure 6.13. Bending of the semiconductor bands at the onset of strong inversion. The surface potential Fs is twice the value of Ff in the neutral p material. Since the equilibrium electron concentration is, we can easily relate the electron concentration at any x to this value. And similarly for holes. At any x, we could combine these equations with Poisson's equation, 619, and the usual charge density expression, 620, to solve for h, x. Let us solve this equation to determine the total integrated charge per unit area, Qs, as a function of the surface potential, Hs. Substituting EQs 616, 617, and 618, for the electron and hole concentrations in EQs 619 and 620, we get. It should be kept in mind that is the electric field, at a depth x. Integrating EQ 621, from the bulk, where the bands are flat, the electric fields are zero, and the carrier concentrations are determined solely by the doping, toward the surface, we get. After integration, we then get. A particularly important case is at the surface, x equals 0, where the surface perpendicular electric field, S, becomes. Where we have introduced a new term, the Debye screening length. The Debye length is a very important concept in semiconductors. It gives us an idea of the distance scale in which charge imbalances are screened or smeared out. For example, if we think of inserting a positively charged sphere in an n-type semiconductor, we know that the mobile electrons will crowd around the sphere. If we move away from the sphere by several Debye lengths, the positively charged sphere and the negative electron cloud will look like a neutral entity. Not surprisingly, LD depends inversely on doping because the higher the carrier concentration, the more easily screening takes place. For n-type material we should use N0 in EQ 625. By using Gauss's law at the surface, we can relate the integrated space charge per unit area to the electric displacement, keeping in mind that the electric field or displacement deep in the substrate is zero. The space charge density per unit area Qs in EQ 626, is plotted as a function of the surface potential Hs in Fig 614. We see from EQ 624, and Fig 614 that when the surface potential is zero, flat band conditions, the net space charge is zero. This is because the fixed dopant charges are cancelled by the mobile carrier charges at flat band. When the surface potential is negative, it attracts and forms an accumulation layer of the majority carrier holes at the surface. The first term in EQ 624 is the dominant one, and the accumulation space charge increases very strongly, exponentially, with negative surface potential. Figure 614. Variations of space charge density in the semiconductor as a function of the surface potential Fs, for p-type silicon with acceptor density 4000 trillions per cubic centimeter at room temperature. P and N are hole and electron concentration at the surface. Ff is the potential difference between the Fermi level and the intrinsic level of the bulk. It is easy to see why by looking at EQ 618, which gives the surface hole concentration in a p-type semiconductor as a function of surface potential. Since the band bending decreases as a function of depth, the integrated accumulation charge involves averaging over depth and introduces a factor of 2 in the exponent. Mathematically, this is due to the square root in EQ. 624. It must be noted that since this charge is due to the mobile majority carriers, holes in this case, the charge piles up near the oxide-silicon interface, since typical accumulation layer thicknesses are 20 nanometers. Also, because of the exponential dependence of accumulation charge on surface potential, the band bending is generally small or is said to be pinned to nearly zero. On the other hand, for a positive surface potential, we see from EQ. 624, that initially the second, linear, term is the dominant one. Although the exponential term exp, QHS is very large, it is multiplied by the ratio of the minority to majority carrier concentration, which is very small, and is initially negligible. Hence, the space charge for small positive surface potentials increases as 2hs as shown in Fig 614. As discussed in detail later in this section, this corresponds to the depletion region charge due to the exposed, fixed immobile dopants, acceptors in this case. The depletion width typically extends over several hundred nanometers. At some point, the band bending is twice the Fermi potential HF, which is enough for the onset of strong inversion. Now, the exponential term exp, QHS, inverse, multiplied by the minority carrier concentration N0 is equal to the majority carrier concentration P0. Hence, for band bending beyond this point, it becomes the dominant term. As in the case of accumulation, the mobile inversion charge now increases very strongly with bias, as indicated by EQ. 617, and shown in Fig 614. The typical inversion layer thicknesses are 5 nanometers, and the surface potential now is essentially pinned at 2hf. It may be pointed out that in accumulation, and especially in inversion, the carriers are confined in the x direction in narrow, essentially triangular potential wells, causing quantum mechanical particle in a box states or subins, similar to those discussed in Chapter 2. However, the carriers are free in the other directions, parallel to the oxide-silicon interface. This leads to a two-dimensional electron gas, 2, DeG, or hole gas, with a staircase constant density of states, as discussed in Appendix 4. The detailed analysis of these effects is, unfortunately, beyond the scope of our discussion here. The charge distribution, electric field, and electrostatic potential for the inverted surface are sketched in Fig 615. For simplicity we use the depletion approximation of Chapter 5 in this figure, assuming complete depletion for 06x6W, and neutral material for x7W. In this approximation the charge per unit area6 due to uncompensated acceptors in the depletion region is, Gna. The positive charge Qm on the metal is balanced by the negative charge Qs in the semiconductor, which is the depletion layer charge plus the charge due to the inversion region Qn. The width of the inversion region is exaggerated in Fig 615 for illustrative purposes. Actually, the width of this region is generally less than 100 angstroms. Thus we have neglected it in sketching the electric field and potential distribution. In the potential distribution diagram we see that an applied voltage V appears partially across the insulator, Vi, and partially across the depletion region of the semiconductor, Hs. Figure 615. Approximate distributions of charge, electric field, and electrostatic potential in the ideal metal oxide semiconductor capacitor in inversion. The relative width of the inverted region is exaggerated for illustrative purposes, but is neglected in the field and potential diagrams. The sepals of the band edges reflect the electric fields in the gate dielectric and the semiconductor channel. The product of the perpendicular electric field and dielectric constant, known as displacement, is continuous across the dielectric semiconductor interface, if there are no changes at the interface, according to Maxwell's boundary conditions. The voltage across the insulator is obviously related to the charge on either side, divided by the capacitance. where pi is permittivity of the insulator and Ci is the insulator capacitance per unit area. The charge Qs will be negative for the n-channel, giving a positive Vi. Using the depletion approximation, we can solve for W as a function of Hs, Prob 6.7. The result is the same as would be obtained for an N plus P junction in Chapter 5, for which the depletion region extends almost entirely into the P region. This depletion region grows with increased voltage across the capacitor until strong inversion is reached. After that, further increases in voltage result in stronger inversion rather than in more depletion. Thus the maximum value of the depletion width is, using EQ 615. We know the quantities in this expression, so Wm can be calculated. The charge per unit area in the depletion region Qd at strong inversion is. The applied voltage must be large enough to create this depletion charge plus the surface potential Hs, inverse. The threshold voltage required for strong inversion, using EQs 615, 628, and 629, is. This assumes the negative charge at the semiconductor surface Qs at inversion is mostly due to the depletion charge Qd. The threshold voltage represents the minimum voltage required to achieve strong inversion, and is an extremely important quantity for most transistors. We will see in the next section that other terms must be added to this expression for real MOS structures. The capacitance voltage characteristics of this ideal MOS structure, Fig 616, vary depending on whether the semiconductor surface is in accumulation, depletion, or inversion. Since the capacitance for MOSFETs is voltage dependent, we must use the more general expression in EQ 555, for the voltage dependent semiconductor capacitance. Actually, if one looks at the electrical equivalent circuit of a MOS capacitor or MOSFET, it is the series combination of a fixed, voltage-independent gate oxide, insulator, capacitance, and a voltage-dependent semiconductor. Capacitance defined according to EQ 634, such that the overall MOS capacitance becomes voltage-dependent. The semiconductor capacitance itself can be determined from the slope of the Qs versus Hs plot, Fig 614. It is clear that the semiconductor capacitance in accumulation is very high because the slope is so steep, that is, the accumulation charge changes a lot with surface potential. Hence, the series capacitance in accumulation is basically the insulator capacitance, Ci. Since, for negative voltage, holes are accumulated at the surface, Fig 612b, the MOS structure appears almost like a parallel plate capacitor, dominated by the insulator property Ci equal pi/d, point 1 in Fig 616. As the voltage becomes less negative, the semiconductor surface is depleted. Thus a depletion layer capacitance Cd is added in series with Ci. Figure 616. Capacitance voltage relation for an N-channel, P, substrate, metal oxide semiconductor capacitor. The dashed curve for voltage is observed at high measurement frequencies. The flat band voltage will be discussed in section 6.4.3. When the semiconductor is in depletion, the semiconductor capacitance Cs is denoted as Cd, where P, S is the semiconductor permittivity and W is the width of the depletion layer from EQ 630. The total capacitance is the capacitance decreases as W grows from flat band, point 2, past weak inversion, point 3, until finally strong inversion is reached at Vt, point 4. In the depletion region, the small signal semiconductor capacitance is given by the same formula EQ 634, which gives the variation of the depletion space charge with surface potential. Since the charge increases as 2Hs, the depletion capacitance will obviously decrease as 1/2Hs, exactly as for the depletion capacitance of a PN junction CEQ 563. After inversion is reached, the small signal capacitance depends on whether the measurements are made at high, typically 1 MHz, or low, typically 1 to 100 Hz, frequency, where high and low are with respect to the generation recombination rate of the minority carriers in the inversion layer. If the gate voltage is varied rapidly, the charge in the inversion layer cannot change in response, and thus does not contribute to the small signal AC capacitance. Hence, the semiconductor capacitance is at a minimum, corresponding to a maximum depletion width. On the other hand, if the gate bias is changed slowly, there is time for minority carriers to be generated in the bulk, drift across the depletion region to the inversion layer, or go back to the substrate and recombine. Now, the semiconductor capacitance, using the same EQ 634, is very large because we saw in Fig 614 that the inversion charge increases exponentially with Hs. Hence, the low-frequency MOS series capacitance in strong inversion is basically Ci once again, 0.5. What is the frequency dependence of the capacitance in accumulation, Fig 612a? We get a very high capacitance both at low and high frequencies because the majority carriers in the accumulation layer can respond much faster than minority carriers. While minority carriers respond on the time scale of enumeration recombination times, typically hundreds of microseconds in SI, majority carriers respond on the time scale of the dielectric relaxation time, Td equal Tp, where T is the resistivity and P is the permittivity. Td is analogous to the RC time constant of a system, and is small for the majority carriers, 0.0001 nanoseconds. As an interesting aside, it may be pointed out that in inversion, although the high-frequency capacitance for MOS capacitors is low, it is high, equal Ci, for MOSFETs because now the inversion charge can flow in readily and very fast, Td, from the source/drain regions rather than having to be created by generation recombination in the bulk. Effects of real surfaces. When MOS devices are made using typical materials, for example, metal high-K silicon dioxide, silicon, departures from the ideal case described in the previous section can strongly affect VT and other properties. First, there is a work function difference between the metal gate and substrate, which depends on the substrate doping. Second, there are inevitably charges at the silicon high-K/silicon dioxide interface and within the oxide which must be taken into account. Figure 617. Variation of the metal semiconductor work function potential difference F with substrate doping concentration, for polysilicon. Work function difference. We expect Fs to vary depending on the doping of the semiconductor. Figure 617 illustrates the work function potential difference Fms equal Fm, Fs for N plus polysilicon on silicon as the doping is varied. For other metal electrodes, the work function of that metal, Fm, must be used. We note that Fms is always negative for this case, and is most negative for heavily doped p-type silicon, i.e., for F close to the valence band. If we try to construct an equilibrium diagram with Fms negative, Fig 618a, we find that in aligning F we must include a tilt in the oxide conduction band, implying an electric field. Thus the metal is positively charged and the semiconductor surface is negatively charged at equilibrium, to accommodate the work function difference. As a result, the bands bend down near the semiconductor surface. In fact, if Fms is sufficiently negative, an inversion region can exist with no external voltage applied. To obtain the flat band condition pictured in Fig 618b, we must apply a negative voltage to the metal, VFB equal Fms. Interface charge. In addition to the work function difference, the equilibrium MOS structure is affected by charges in the insulator and at the semiconductor oxide interface, Fig 619. For example, alkali metal ions, particularly Na+, can be incorporated inadvertently in the oxide during growth or subsequent processing steps. Since sodium is a common contaminant, it is necessary to use extremely clean chemicals, water, gases, and processing environment to minimize its effect on dielectric layers. Sodium ions introduce positive charges, Qm, in the oxide, which in turn induce negative charges in the semiconductor. The effect of such positive ionic charges in the oxide depends upon the number of ions involved and their distance from the semiconductor surface, Prop 6.14. Figure 6.18 Effect of a negative work function difference A, band bending and formation of negative charge at the semiconductor surface, B, achievement of the flat band condition by application of a negative voltage. The negative charge induced in the semiconductor is greater if the Na+ ions are near the interface than if they are farther away. The effect of this ionic charge on threshold voltage is complicated by the fact that Na+ ions are relatively mobile in silicon dioxide, particularly at elevated temperatures, and can thus drift in an applied electric field. Obviously, a device with threshold voltage dependent on its past history of voltage bias is unacceptable. Fortunately, Na contamination of the oxide can be reduced to tolerable levels by proper care in processing. The oxide also contains trapped charges, COT, due to imperfections in the silicon dioxide. In addition to oxide charges, a set of positive charges arises from interface states at the silicon dioxide interface. These charges, which we will call KIT, result from the sudden termination of the semiconductor crystal lattice at the oxide interface. Near the interface is a transition layer, oxidized silicon, containing fixed charges, QF. As oxidation takes place in forming the silicon dioxide layer, silicon is removed from the surface and reacts with the oxygen. When the oxidation is stopped, some ionic Si is left near the interface. These ions, along with uncompleted silicon bonds at the surface, result in a sheet of positive charge QF near the interface. This charge depends on oxidation rate and subsequent heat treatment, and also on crystal orientation. For carefully treated silicon dioxide interfaces, typical charge densities due to KIT and QF are about 10 billion charge SPE or square centimeter for samples with 100 surfaces. The interface charge density is about a factor of 10 higher on 111 surfaces. That is why most devices are generally made on 100 silicon. For simplicity, we will include the various oxide and interface charges in an effective positive charge at the interface G, coulombs per square centimeter. The effect of this charge is to induce an equivalent negative charge in the semiconductor. Thus an additional component must be added to the flat band voltage. Since the difference in work function and the positive interface charge both tend to bend the bands down at the semiconductor surface, a negative voltage must be applied to the metal relative to the semiconductor to achieve the flat band condition of Fig 619b. Threshold voltage. The voltage required to achieve flat band should be added to the threshold voltage equation, 633, obtained for the ideal MOS structure, for which we assumed a zero flat band voltage. Thus the voltage required to create strong inversion must be large enough to first achieve the flat band condition, Ms and Chi/Ci terms, then accommodate the charge in the depletion region, Qd/Ci, and finally to induce the inverted region, 2HF. This equation accounts for the dominant threshold voltage effects in typical MOS devices. It can be used for both N-type and P-type substrates 8 if appropriate signs are included for each term, Fig 620. Typically FMS is negative, although its value varies as in Fig 617. The interface charge is positive, so the contribution of the Chi/Ci term is negative for either substrate type. On the other hand, the charge in the depletion region is negative for ionized acceptors, P-type substrate, N-channel device, and is positive for ionized donors, N-type substrate, P-channel. Figure 620. Influence of materials parameters on threshold voltage. A. The threshold voltage equation indicating signs of the various contributions. B. Variation of threshold voltage with substrate doping for N-channel and P-channel polysilicon dioxide silicon devices. Also, the term HF, which is defined as EI, F, Q in the neutral substrate, can be positive or negative, depending on the conductivity type of the substrate. Considering the signs in Fig 620, we see that all four terms give negative contributions in the P-channel case. Thus we expect negative threshold voltages for typical p-channel devices. On the other hand, n-channel devices may have either positive or negative threshold voltages, depending on the relative values of terms in EQ. 638. All terms in EQ. 638, except Chi/Ci depend on the doping in the substrate. The terms Ms and Hf have relatively small variations as F is moved up or down by the doping. Large changes can occur in Qd, which varies with the square root of the doping impurity concentration as in EQ. 632. We illustrate the variation of threshold voltage with substrate doping in Fig 620. As expected from EQ. 638, Vt is always negative for the p-channel case. In the n-channel case, the negative flat band voltage terms can dominate for lightly doped p-type substrates, resulting in a negative threshold voltage. However, for more heavily doped substrates, the increasing contribution of Na to the Qd term dominates, and Vt becomes positive. We should pause here and consider what positive or negative Vt means for the two cases. In a p-channel device we expect to apply a negative voltage from metal to semiconductor in order to induce the positive charges in the channel. In this case a negative threshold voltage means that the negative voltage we apply must be larger than Vt in order to achieve strong inversion. In the n-channel case we expect to apply a positive voltage to the metal to induce the channel. Thus a positive value for Vt means the applied voltage must be larger than this threshold value to obtain strong inversion and a conducting n-channel. On the other hand, a negative threshold voltage in this case means that a channel exists at V equals 0 due to the FMS and Chi effects, Fig 618 and 619, and we must apply a negative voltage Vt to turn the device off. Since lightly doped substrates are desirable to maintain a high breakdown voltage for the drain junction, Fig 620 suggests that Vt will be negative for n-channel devices made by standard processing. This tendency for the formation of depletion mode, normally on, n-channel transistors is a problem which must be dealt with by special fabrication methods to be described in section 6.5.5. MOS capacitance voltage analysis. Let us see how the various parameters of a MOS device such as insulator thickness, substrate doping, and threshold voltage can be determined from the current voltage characteristics, Fig 621a. First, the shape of the current voltage curve depends upon the type of substrate doping. If the high-frequency capacitance is large for negative gate biases and small for positive biases, it is a p-type substrate, and vice versa. From the low-frequency current voltage curve for p-type material, as the gate bias is made more positive, or less negative, the capacitance goes down slowly in depletion and then rises rapidly in inversion. As a result, the low-frequency current voltage is not quite symmetric in shape. For n-type substrates, the current voltage curves would be the mirror image of Fig 621. Figure 621. Fast interface state determination, A. High frequency and low frequency current voltage curves showing impact of fast interface states, B. Energy levels in the band gap due to fast interface states, C. Equivalent circuit of metal oxide semiconductor structure showing capacitance components due to gate oxide, depletion layer in the channel, and fast interface states. The capacitance Ci equal pi/d in accumulation or strong inversion, at low frequencies, gives us the insulator thickness, d. The minimum MOS capacitance, min, is the series combination of Ci and the minimum depletion capacitance, min equal Ps/Wm, corresponding to the maximum depletion width. We can in principle use the measurement of min to determine the substrate doping. However, from EQ 631, we see that the dependence of Wm on Na is complicated, and we get a transcendental equation which can only be solved numerically. Actually, an approximate, iterative solution exists which gives us Na. In terms of the minimum depletion capacitance, Cd minimum, where Cd min is in f/cm². Once the substrate doping is obtained, we can determine the flat band capacitance from it. It can be shown that the semiconductor capacitance at flat band CFB, 0.2 in Fig 616, is determined from the debye length. Capacitance, where the debye length is dependent on doping as described in EQ 625. The overall Mohs flat band capacitance, CFB, is the series combination of C debye and Ci. We can thus determine VFB corresponding to the CFB. Once Ci, VFB, and substrate doping are obtained, all terms in the threshold voltage expression, EQ 638, are known. Interestingly, the threshold voltage Vt does not correspond to exactly the minimum of the current voltage characteristics, Min, but a slightly higher capacitance marked as 0.4 in Fig 616. In fact, it corresponds to the series combination of Ci and 2CdMin, rather than the series combination of Ci and Min. The reason for this is that when we change the gate bias around strong inversion, the change of charge in the semiconductor is the sum of the change in depletion charge and the mobile inversion charge, where the two are equal in magnitude at the onset of strong inversion. We can also determine Mohs parameters such as the fast interface state density, DID, and mobile ion charges, QM, from current voltage measurements, Fig 621b, C and 622. The term fast interface state refers to the fact that these defects can change their charge state relatively fast in response to changes of the gate bias. As the surface potential in a Mohs device is varied, the fast interface states or traps in the band gap can move above or below the Fermi level in response to the bias, because their positions relative to the band edges are fixed, Fig 621b. Figure 622. Mobile ion determination, A. Movement of mobile ions due to positive and negative bias temperature stress, B. Current voltage characteristics under positive, dashed line, and negative, solid line, bias temperature. Keeping in mind the property of the Fermi-Dirac distribution that energy levels below the Fermi level have a high probability of occupancy by electrons, while levels above the Fermi level tend to be empty, we see that a fast interface state moving above the Fermi level would tend to give up its trapped electron to the semiconductor, or equivalently capture a hole. Conversely, the same fast interface state below the Fermi level captures an electron, or gives up a hole. It obviously makes sense to talk in terms of electrons or holes, depending on which is the majority carrier in the semiconductor. Since charge storage results in capacitance, the fast interface states give rise to a capacitance which is in parallel with the depletion capacitance in the channel, and hence is additive, and this combination is in series with the insulator capacitance Ci. The fast interface states can keep pace with low frequency variations of the gate bias, 1 Hz to 1000 Hz, but not at extremely high frequencies, 1 MHz. So the fast interface states contribute to the low frequency capacitance CLF, but not the high frequency capacitance CHF. Clearly, from the difference between the two, we ought to be able to compute the fast interface state density. We will not do the detailed derivation here. It can be shown that while the fast interface states can respond quickly to voltage changes, the fixed oxide charges QF, as the name implies, do not change their charge state regardless of the gate bias or surface potential. As mentioned above, the effect of these charges on the flat band and threshold voltage depends not only on the number of charges but also their location relative to the oxide-silicon interface, Fig 622a. Hence, we must take a weighted sum of these charges, counting charges closer to the oxide-silicon interface more heavily than those that are farther away. This position dependence is the basis of what is called the bias temperature stress test for measuring the mobile ion content, QM. We heat up the Mohs device to 200300 degrees C, to make the ions more mobile, and apply a positive gate bias to generate a field of 1 MV per centimeter within the oxide. After cooling the capacitor to room temperature, the current voltage characteristics are measured. We have seen how VFB can be determined from the current voltage curve, using EQ 640, and Ci. VFB is also given by EQ 637. The positive bias repels positive mobile ions such as sodium to the oxide-silicon interface so that they contribute fully to a flat band voltage we can call VFB+. Next, the capacitor is heated up again, a negative bias is applied so that the ions drift to the gate electrode, and another current voltage measurement is made. Now, the mobile ions are too far away to affect the semiconductor band bending, but induce an equal and opposite charge on the gate electrode. From the resulting current voltage, the new flat band, VFB, is determined. From the difference of the two flat band voltages, we can determine the mobile ion content using time-dependent capacitance measurements. During current voltage measurements, if the gate bias is varied rapidly from accumulation to inversion, the depletion width can momentarily become greater than the theoretical maximum for gate biases beyond threshold voltage. This phenomenon is known as deep depletion, and causes the MOS capacitance to drop below the theoretical minimum, min, for a transient period. After a time period characteristic of the minority carrier lifetime, which determines the rate of generation of the minority carriers in the MOS device, the depletion width collapses back to the theoretical maximum and the capacitance recovers to min, Fig 623. This capacitance transient, CT, forms the basis of a powerful technique to measure the lifetime, known as the Zerbst technique. Figure 623. Time-dependent metal oxide semiconductor capacitance due to the application of a step voltage VA, which puts the capacitor in accumulation, to VI, which puts the capacitor in inversion. Current voltage characteristics of MOS gate oxides. An ideal gate insulator does not conduct any current, but for real insulators there can be some leakage current which varies with the voltage or electric field across the gate oxide. By looking at the band diagram of the MOS system perpendicular to the oxide-silicon interface, Fig 624, we see that for electrons in the conduction band, there is a barrier, EC, equal 3.1 eV. Although electrons with energy less than this barrier cannot go through the oxide classically, it was discussed in Chapter 2 that quantum mechanically electrons can tunnel through a barrier, especially if the barrier thickness is sufficiently small. The detailed calculation of the Fowler-Nordheim tunneling. Current for electrons going from the silicon conduction band to the conduction band of silicon dioxide, and then having the electrons hop along in the oxide to the gate electrode, involves solving the Schrödinger equation for the electron wave function. The Fowler-Nordheim tunneling current IFN can be expressed as a function of the electric field in the gate oxide, where B is a constant depending on m*n and the barrier height. Figure 624. Current voltage characteristics of gate oxides, A. Fowler-Nordheim and direct tunneling through thin gate oxides, B. Plot of Fowler-Nordheim tunneling leakage current as a function of electric field across the oxide. As gate oxides are made thinner in successive generations of MOSFETs, the tunneling barrier in the gate oxide becomes so thin that the electrons in the conduction band of Si can tunnel through the gate oxide and emerge in the gate, without having to go via the conduction band of the gate oxide. This is known as direct tunneling rather than Fowler-Nordheim tunneling. The overall physics is similar, but some of the details are different. For instance, Fowler-Nordheim tunneling involves a triangular barrier, while direct tunneling is through a trapezoidal barrier, Fig 624a. Such tunneling currents are becoming a major problem in modern devices because the useful feature of high input impedance for most devices is degraded. It is necessary to increase the gate capacitance in successive generations of MOSFETs in order to increase the drain current, as discussed later in section 6.5. One can achieve higher CI by using insulators with a dielectric constant higher than silicon dioxide instead of reducing the gate oxide thickness, D, as can be seen from EQ 629. The advantage of not reducing D too much is that it keeps the tunneling barrier wide, and the gate oxide field low, thereby keeping the gate tunneling leakage current low. EQ 643. Such high dielectric constant insulators such as hafnium dioxide, are also known as high K gate dielectrics because K is also sometimes used as a symbol for dielectric constant. Prolonged charge transport through gate oxides can ultimately cause catastrophic electrical breakdown of the oxides. This is known as time-dependent dielectric breakdown, TDDB. One of the popular models that explains this degradation involves electrons tunneling into the conduction band of the gate oxide from the negative electrode, cathode, then gaining energy from the electric field, thus becoming hot electrons in the gate oxide. If they gain sufficient energy, they can cause impact ionization within the oxide and create electron-hole pairs, EHPs. The electrons are accelerated toward the positive silicon substrate, while the holes travel toward the gate. However, electron and hole mobilities are extremely small in silicon dioxide. Hole mobilities are particularly low, 0.01 square centimeters per volt. Hence, there is a great propensity for these impact-generated holes to be trapped at defect sites within the oxide, near the cathode. The resulting band diagram, Fig 625, is altered by the sheet of trapped positive charge, which causes the internal electric field between this point and the gate to increase. A similar distortion of the electric field near the Si anode is created by the trapped impact-generated electrons. However, the steepest slope in Fig 625, and therefore the highest field, is near the gate. As a result, the barrier for electron tunneling from the gate into the oxide is reduced. More electrons can tunnel into the oxide, and cause more impact ionization. We get a positive feedback effect that can lead to a runaway TDDB process. With high K gate dielectrics, other degradation mechanisms occur, such as negative bias temperature instability, NBTI, in PMOSFETs. The negative gate voltage that must be applied to turn the PMOSFET on causes breakage of silicon hydride bonds near the gate dielectric interface and hole trapping in the gate dielectric. Similarly, one can have PBTI in NMOSFETs, although those effects are experimentally found to be less severe. Figure 625. Time-dependent dielectric breakdown of oxides, band diagram of a metal oxide semiconductor device showing the band edges in the polysilicon gate, oxide, and silicon substrate. Trapped holes and electrons in the oxide distort the band edges, and increase the electric field in the oxide near the gate. The tunneling barrier width is seen to be less than if there were no charge trapping, dashed line. The MOS transistor is also called a surface field effect transistor, since it depends on control of current through a thin channel at the surface of the semiconductor, Fig 610. When an inversion region is formed under the gate, current can flow from drain to source, for an N-channel device. In this section we analyze the conductance of this channel and find the drain current, drain voltage characteristics as a function of gate voltage Vg. As in the GFET case, we will find these characteristics below saturation and then assume drain current remains essentially constant above saturation. Output characteristics. The applied gate voltage Vg is accounted for by EQ 628, plus the voltage required to achieve flat band. The induced charge Qs in the semiconductor is composed of mobile charge Qn and fixed charge in the depletion region Qd. Substituting Qn plus Qd for Qs, we can solve for the mobile charge. At threshold the term in brackets can be written Vg, Vt from EQ 638. With a voltage Vd applied, there is a voltage rise Vx from the source to each point x in the channel. Thus the potential Hs, x, is that required to achieve strong inversion, 2Hf, plus the voltage Vx. If we neglect the variation of Qd, x, with bias Vx, EQ 646, can be simplified to. This equation describes the mobile charge in the channel at point x, Fig 626. The conductance of the differential element dx is on Qn, x, z dx, where z is the width of the channel and on is a surface electron mobility, indicating. The mobility in a thin region near the surface is not the same as in the bulk material. At point x we have Figure 626. Schematic view of the N-channel region of a metal oxide semiconductor transistor under bias below pinch-off, and the variation of voltage, along the conducting channel. Integrating from source to drain. Where determines the conductance and transconductance of the N-channel MOSFET CEQs. 651, and 654. In this analysis, the depletion charge QD in the threshold voltage VT is simply the value with no drain current. This is an approximation, since QD, X, varies considerably when VD is applied, to reflect the variation in Vx, see Fig 626b. However, EQ 649 is a fairly accurate description of drain current for low values of VD, and is often used in approximate design calculations because of its simplicity. A more accurate and general expression is obtained by including the variation of QD, X. Performing the integration of EQ 648, using EQ 646, for Qn, X, one obtains. The drain characteristics that result from these questions are shown in Fig 610c. If the gate voltage is above threshold, Vg is greater than Vt, the drain current is described by EQ 650, or approximately by EQ 649, for low drain voltage. Initially the channel appears as an essentially linear resistor, dependent on gate voltage. The conductance of the channel in this linear region can be obtained from EQ 649, with Vd, Vg, Vt, where gate voltage is greater than threshold voltage for a channel to exist. As the drain voltage is increased, the voltage across the oxide decreases near the drain, and Qn becomes smaller there. As a result, the channel becomes pinched off at the drain end, and the current saturates. The saturation condition is approximately given by the drain current at saturation remains essentially constant for larger values of drain voltage. Substituting EQ 652 into EQ 649, we obtain for the approximate value of drain current at saturation. The transconductance in the saturation range can be obtained approximately by differentiating EQ 653 with respect to the gate voltage. The derivations presented here are based on the N-channel device. For the P-channel enhancement transistor, the voltages Vd, Vg, and Vt are negative, and current flows from source to drain, Fig 627. Transfer characteristics. The output characteristics plot the drain current as a function of the drain bias, with gate bias as a parameter, Fig 627. On the other hand, the transfer characteristics plot the output drain current as a function of the input gate bias, for fixed drain bias, Fig 628a. Clearly, in the linear region, drain current versus gate voltage should be a straight line from EQ 649. The intercept of this line on the gate voltage axis is the linear region threshold voltage, Vt, ln, and the slope, divided by the applied Vd, gives us the linear value of Kn, ln, of the N-channel MOSFET. Figure 6-27. Drain current voltage characteristics for enhancement transistors. A. For N-channel drain voltage, gate voltage, threshold voltage, and drain current are positive. B. For P-channel all these quantities are negative. If we look at actual data, however, we see that while the characteristics are approximately linear at low gate bias, at high gate biases the drain current increases sublinearly. The transconductance, Gm, ln, in the linear region can be obtained by differentiating the right-hand side of EQ 649, with respect to gate bias. The Gm, ln, is plotted as a function of Vg in Fig 628b. It may be noted that the transconductance is zero below threshold voltage because there is little drain current. It goes through a maximum at the point of inflection of the ID, Vg curve, and then decreases. This decrease is due to two factors that will be discussed in section 6.5.3 and 6.5.8, Degradation of the effective channel mobility as a function of increasing transverse electric field across the gate oxide, and source/drain series resistance. For the transfer characteristics in the saturation region, since EQ 653 shows a quadratic dependence of ID on Vg, we get a linear behavior by plotting not the drain current, but rather the square root of ID, as a function of Vg, Fig 629. Figure 628. Linear region transfer characteristics, A. Plot of drain current versus gate voltage for metal oxide semiconductor field effect transistor in the linear region, B. Transconductance as a function of gate bias. Figure 629. Saturation region transfer characteristics, plot of square root of the drain current versus gate voltage for metal oxide semiconductor field effect transistor. In this case the intercept gives us the threshold voltage in the saturation region, Vt, sat. We shall see in section 6.5.10 that due to effects such as drain-induced barrier lowering, DIBL, for short channel length MOSFETs the Vt, sat, can be lower than Vt, ln, while the long channel values are similar. Similarly, the slope of the transfer characteristics can be used to determine the value of Kn in the saturation region, Kn, sat, for the N-channel MOSFET, which can be different from Kn, ln, for short channel devices. For an N-channel MOSFET with a gate oxide thickness of 10 nanometers, threshold voltage equals 0.6 volts, and Z equal 25 micrometers, L equal 1 micrometer. Calculate the drain current at gate voltage equal 5 volts and drain voltage equal 0.1 volts. Repeat for gate voltage equal 3 volts and drain voltage equal 5 volts. Discuss what happens for drain voltage equal 7 volts. Assume an electron channel mobility of on equal 200 square centimeters per volt. For gate voltage equal 5 volts and drain voltage equal 0.1 volts, and threshold voltage equal 0.6 volts, drain voltage is less than gate voltage minus threshold voltage, we are in the linear region. Thus, for Vd equals 7V, ID will not increase, because we are in the saturation region. Mobility models. The mobility of carriers in the channel of a MOSFET is lower than in bulk semiconductors because there are additional scattering mechanisms. Since carriers in the channel are very close to the semiconductor oxide interface, they are scattered by surface roughness and by coulombic interaction with fixed charges in the gate oxide. When the carriers travel in the inversion layer from the source to the drain, they encounter microscopic roughness on an atomistic scale at the oxide-silicon interface and undergo scattering because, as discussed in section 3.4.1, any deviation from a perfectly periodic crystal potential results in scattering. This mobility degradation increases with the gate bias because a higher gate bias draws the carriers closer to the oxide-silicon interface, where they are more influenced by the interfacial roughness. It is very interesting to note that if we plot the effective carrier mobility in the MOSFET as a function of the average transverse electric field in the middle of the inversion layer, we get what is known as a universal mobility degradation curve for any MOSFET, which is independent of the technology or device structural parameters such as oxide thickness and channel doping, Fig 630. Figure 630. Inversion layer electron mobility versus effective transverse field, at various temperatures. The triangles, circles, and squares refer to different metal oxide semiconductor field effect transistors with different gate oxide thicknesses and channel dopings. Figure 631. Determination of effective transverse field. Idealized charge distribution and transverse electric field in the inversion layer and depletion layer, as a function of depth in the channel of a metal oxide semiconductor field effect transistor. The region to which we apply Gauss' law is shown in color. We can apply Gauss's law to the region marked by the colored box in Fig 631, which encloses all the depletion charge and half of the inversion charge in the channel. We see that the average transverse field in the middle of the inversion region is given by. While this model works quite well for electrons, for reasons that are not clearly understood at present, it has to be modified slightly for holes in the sense that the average transverse field must now be defined as. This degradation of mobility with gate bias is often compactly described by writing the drain current expression as, where U is called the mobility degradation parameter. Because of the additional, Vg, Vt, term in the denominator, the drain current increases sublinearly with gate bias for high gate voltages. In addition to this dependence of the channel mobility on gate bias or transverse electric field, there is also a strong dependence on drain bias or the longitudinal electric field. As shown in Fig 324, the carrier drift velocity increases linearly with electric field, ohmic behavior, until the field reaches E saturation. In other words, the mobility is constant up to E saturation. After this, the velocity saturates at Vs, and it can no longer be described in terms of mobility. These effects can be described as: the maximum longitudinal electric field near the drain end of the channel is approximately given by the voltage drop along the pinch-off region, Vd, Sat, divided by the length of the pinch-off region, L. From a two-dimensional solution of the Poisson equation near the drain end, one can show that the pinch-off region L shown in Fig 611c is approximately equal to 2,3 dxj, where d is the gate oxide thickness and xj is the source/drain junction depth. The factor of 3 is due to the ratio of the dielectric constant for silicon to that of silicon dioxide. Short channel MOSFET current voltage characteristics. In short channel devices, the analysis has to be somewhat modified. As mentioned in the previous section, the effective channel mobility decreases with increasing transverse electric field perpendicular to the gate oxide, i.e., the gate bias. Furthermore, for very high longitudinal electric fields in the pinch-off region, the carrier velocity saturates, Fig 324. For short channel lengths, the carriers travel at the saturation velocity over most of the channel. In that case, the drain current is given by the width times the channel charge per unit area times the saturation velocity. As a result, the saturation drain current does not increase quadratically with Vg, Vt, as shown in EQ 653, but rather shows a linear dependence. Note the equal spacing of curves in Fig 632. Due to the advances in SI device processing, particularly photolithography, metal oxide semiconductor field effect transistors used in modern integrated circuits tend to have short channels, and are commonly described by EQ 660, rather than EQ 653. Current generation nanoscale MOSFET channel lengths have been scaled down so aggressively that we have entered a different regime of operation where there are very few scattering events in the channel. This is known as the ballistic or quasi-ballistic regime. The terminology comes from the analogy with launching electrons in the channel where they travel unimpeded like ballistic missiles. Under these conditions, the current is not limited by velocity saturation, which is caused by optical phonon scattering, in the pinch-off region near the drain, as described in EQ 660. Instead, the current is limited by how rapidly the carriers can be supplied by the source. This is known as source injection limited transport. Figure 632. Experimental output characteristics of N-channel and P-channel metal oxide semiconductor field effect transistors with 0.1 micrometer channel lengths. The curves exhibit almost equal spacing, indicating a linear dependence of drain current on gate voltage, rather than a quadratic dependence. We also see that drain current is not constant but increases somewhat with drain voltage in the saturation region. The P-channel devices have lower currents because hole mobilities are lower than electron mobilities. Under these conditions, the drain current is given by where R is the reflection coefficient of the electron wave function near the top of the channel potential barrier near the source, Fig 633, and Vj is effective source injection velocity. Vj is related to the random thermal velocity, Vth, of the carriers in the source. At high carrier concentrations in the channel, Vj approaches a higher velocity, Vf, which is the velocity of the carriers near the Fermi level. An analysis of the physics by Naderi and Lundstrom has shown that the backscattering or the reflection coefficient R is related to the low field mobility in the channel. The higher the mobility, the longer is the mean free path, leading to a lower R and higher source injection limited drain current. This model of transport of carriers in a nanoscale device treats electrons being transmitted as waves in an electron waveguide, and is known as the Landauer-Buteyker formalism. This is a powerful and different way of treating transport in nanoscale devices where scattering is negligible, and the concept of mobility, which is determined by scattering, is suspect. The Landauer approach treats conductance in terms of transmission of the electron waves. Figure 633. A. Source injection limited quasi-ballistic metal oxide semiconductor field effect transistor. The gate capacitance and drain-to-channel capacitance compete from control of the potential barrier near the source end of the channel at X. B. Channel potential profile for metal oxide semiconductor field effect transistor in equilibrium, and superimposed parabolic band structure. C. Channel potential profile with drain at Vd showing partial transmission of electron waves over top of barrier. Control of threshold voltage. Since the threshold voltage determines the requirements for turning the MOS transistor on or off, it is very important to be able to adjust Vt in designing the device. For example, if the transistor is to be used in a circuit driven by a 3-volt battery, it is clear that a 4-volt threshold voltage is unacceptable. Some applications require not only a low value of Vt, but also a precisely controlled value to match other devices in the circuit. All of the terms in EQ 638 can be controlled to some extent. The work function potential difference FMS is determined by choice of the gate conductor material. 0F depends on the substrate doping. Chi can be reduced by proper oxidation methods and by using silicon grown in the 100 orientation. QD can be adjusted by doping of the substrate, and Ci depends on the thickness and dielectric constant of the insulator. We shall discuss here several methods of controlling these quantities in device fabrication. Choice of gate electrode. Since threshold voltage depends on FMS, the choice of the gate electrode material, i.e., the gate electrode work function, has an impact on the threshold voltage. When metal oxide semiconductor field effect transistors were first made in the 1960s, they used aluminum gates. However, since aluminum has a low melting point, it precluded the use of a self-aligned source/drain technology because that required a high-temperature source/drain implant anneal after the gate formation. Hence, aluminum was supplanted by N+ doped LPCVD polysilicon refractory, high melting point, gates, where the Fermi level lines up with the conduction band edge in silicon. While this works quite well for N-channel metal oxide semiconductor field effect transistors, we shall see in section 9.3.1 that it can create problems for P-channel metal oxide semiconductor field effect transistors. Therefore, sometimes, a P+ doped polysilicon gate is used for P-channel devices. Refractory metal gates with suitable work functions are now being used as replacements for doped polysilicon. One attractive candidate is tungsten, whose work function is such that the Fermi level happens to lie near the midgap of silicon. Control of Ci. Since a low value of Vt and a high drive current is usually desired, a thin oxide layer is used in the gate region to increase Ci equal pi/d in EQ 638. From Fig 620 we see that increasing Ci makes Vt less negative for P-channel devices and less positive for N-channel with QD7 Chi. For practical considerations, the high K gate oxide thickness is generally 10 to 100 angstroms, 1 to 10 nanometers, in modern devices having sub-micron gate length. An example of such a device is shown in Fig 634. The gate oxide, easily observable in this micrograph, is high K. The interfacial layer between the crystalline silicon and the high K is also observable. Although a low threshold voltage is desirable in the gate region of a transistor, a large value of Vt is needed between devices. For example, if a number of transistors are interconnected on a single Si chip, We do not want inversion layers to be formed inadvertently between devices, generally called the field. One way to avoid such parasitic channels is to increase threshold voltage in the field by using a very thick oxide using STI. Figure 635 illustrates a transistor with a gate oxide 10 nanometers thick and a field oxide of 0.5 millimeters. Threshold adjustment by ion implantation. The most valuable tool for controlling threshold voltage is ion implantation, section 5.1.4. Since very precise quantities of impurity can be introduced by this method, it is possible to maintain close control of threshold voltage. The negatively charged boron acceptors serve to reduce the effects of the positive depletion charge QD. As a result, threshold voltage becomes less negative. Similarly, a shallow boron implant into the p-type substrate of an N-channel transistor can make threshold voltage positive, as required for an enhancement device. If the implantation is performed at higher energy, or into the bare Si instead of through an oxide layer, the impurity distribution lies deeper below the surface. In such cases, the essentially Gaussian impurity concentration profile cannot be approximated by a spike at the Si surface. Therefore, effects of distributed charge on the QD term of EQ 638 must be considered. Calculations of the effects on threshold voltage in this case are more complicated, and the shift of threshold voltage with implantation dose is often obtained empirically instead. Figure 634. Cross-section of a metal oxide semiconductor field effect transistor. This high-resolution transmission electron micrograph of a silicon metal oxide semiconductor field effect transistor shows the silicon channel and metal gate separated by a thin silicon high-K gate dielectric. This 45 nanometer PMOS metal gate transistor was made using gate last or replacement metal gate process flow. The implantation energy required for shallow threshold voltage adjustment implants is low, 50 to 100 kilo electron volts, and relatively low doses are needed. A typical threshold voltage adjustment requires only about 10 S of implantation for each wafer, and therefore this procedure is compatible with large-scale production requirements. If the implantation is continued to higher doses, threshold voltage can be moved past zero to the depletion mode condition, Fig 636. This capability provides considerable flexibility to the integrated circuit designer, by allowing enhancement and depletion mode devices to be incorporated on the same chip. For example, a depletion mode transistor can be used instead of a resistor as a load element for the enhancement device. Thus, an array of metal oxide semiconductor transistors can be fabricated in an integrated circuit layout, with some adjusted by implantation to have the desired enhancement mode threshold voltage and others implanted to become depletion loads. As mentioned, threshold voltage control is important not only in the metal oxide semiconductor field effect transistors but also in the isolation or field regions. In addition to using a thick field oxide, we can do a channel stop implant, so called because it stops turning on a parasitic channel in the isolation regions, selectively in the isolation regions under the field oxide, Fig 634. Generally, a B-channel stop implant is used for N-channel devices. It must be noted that such an acceptor implant will raise the field thresholds for N-channel metal oxide semiconductor field effect transistors made in a P substrate, but will decrease the field thresholds for PMOS FETs made in an N substrate. Figure 635. Thin oxide in the gate region and thick oxide in the field between transistors for threshold voltage control. Substrate bias affects the body effect. For a p-channel transistor with a gate oxide thickness of 10 nanometers, calculate the boron ion dose Fb, B+ ions per square centimeter, required to reduce threshold voltage from -1.1 V to 0.5 volts. Assume that the implanted acceptors form a sheet of negative charge just below the silicon surface. If, instead of a shallow boron implant, it was a much broader distribution, how would the threshold voltage calculation change? Assuming a boron ion beam current of 10 to 5 amperes, and supposing that the area scanned by the ion beam is 650 square centimeters, how long does this implant take? Since the boron negative ions are assumed to form a sheet of charge just below the gate oxide, they affect the fixed oxide charge term in VFB. Thus, if the B distribution is deeper, we cannot assume it to be a sheet charge in VFB. If it is approximately constant over the maximum depletion width, we should instead change the substrate doping term in the expression for threshold voltage. Otherwise, the calculation has to be done by numerically solving Poisson's equation in the depletion region, with a varying doping concentration corresponding to the B distribution, to obtain the voltage drop in the semiconductor. For a beam current of 10 mA scanned over a 650 square centimeters target area. In the derivation of EQ 649, for current along the channel, we assumed that the source S was connected to the substrate B, Fig 627. In fact, it is possible to apply a voltage between S and B, Fig 637. With a reverse bias between the substrate and the source, bias voltage negative for an N-channel device, the source channel junction potential barrier, Fig 610b, is increased. Clearly, the gate must be biased more positively than for the grounded substrate, to lower the source channel potential barrier sufficiently to create an inversion layer. This causes the threshold voltage to increase with reverse substrate bias. This is known as the body effect. The new threshold voltage is given by adding a voltage drop, VB, between the gate and the substrate, Fig 637, to the 2HF term in the grounded substrate case, so that EQ 638 should be changed. Figure 636. Typical variation of threshold voltage for a p-channel device with increased implanted boron dose. The originally enhancement p-channel transistor becomes a depletion mode device by sufficient boron implantation. However, since the threshold voltage is defined not with respect to the substrate, but rather with respect to the grounded source, we need to add the bias voltage term at the end, and the bias voltage terms cancel out. The net result is that the depletion region in the channel is widened and the threshold gate voltage required to achieve inversion must be increased to accommodate the larger QD. The change in threshold voltage due to the substrate bias is: if the substrate bias VB is much larger than 20F, typically 0.6 volts, the threshold voltage is dominated by bias voltage and where bias voltage will be negative for the N-channel case. As the substrate bias is increased, the threshold voltage becomes more positive. The effect of this bias becomes more dramatic as the substrate doping is increased, since threshold voltage change is also proportional to square root of acceptor concentration. For a p-channel device, the bulk to source voltage VB is positive to achieve a reverse bias, and the approximate change VT for VBW2HF is Figure 637. Threshold voltage dependence on substrate bias resulting from application of a voltage V from the substrate, bulk, to the source. For N-channel, V must be 0 or negative to avoid forward bias of the source junction. For P-channel, V must be 0 or positive. Thus the P-channel threshold voltage becomes more negative with substrate bias. The substrate bias effect, also called the body effect, increases threshold voltage for either type of device. This effect can be used to raise the threshold voltage of a marginally enhancement device, VT0, to a somewhat larger and more manageable value. This can be an asset for N-channel devices, particularly, see Fig 620. The effect can present problems, however, in MOS integrated circuits for which it is impractical to connect each source region to the substrate. In these cases, possible threshold voltage shifts due to the body effect must be taken into account in the circuit design. Subthreshold characteristics. If we look at the drain current expression EQ 653, it appears that the current abruptly goes to 0 as soon as Vg is reduced to Vt. In reality, there is still some drain conduction below threshold, and this is known as subthreshold conduction. This current is due to weak inversion in the channel between flat band and threshold, for band bending between 0 and 2HF, which leads to a diffusion current from source to drain. the drain current in the subthreshold region is equal to where it can be seen that drain current depends exponentially on gate bias, Vg. However, Vd has little influence once Vd exceeds a few /Q. Obviously, if we plot LNID as a function of gate bias Vg, we should get a linear behavior in the subthreshold regime, as shown in Fig 638a. The slope of this line, or more precisely the reciprocal of the slope, is known as the subthreshold slope, S, which has typical values of 70 mV/decade at room temperature for state-of-the-art metal oxide semiconductor field effect transistors. This means that a change in the input Vg of 70 mV will change the output ID by an order of magnitude. Clearly, the smaller the value of S, the better the transistor is as a switch. A small value of S means a small change in the input bias can modulate the output current considerably. It can be shown that the expression for S is given by. Here, the factor ln10, equal 2.3, is introduced to change from log10 to natural logarithm, ln. This equation can be understood by looking at the electrical equivalent circuit of the MOSFET in terms of the capacitors, Fig 638b. Between the gate and the substrate, we find the gate capacitance, Ci, in series with the parallel combination of the depletion capacitance in the channel, Cd, and the fast interface state capacitance, Cit equal Qdid. The expression in brackets in EQ 666 is simply the capacitor divider ratio, which tells us what fraction of the applied gate bias, Vg, appears at the silicon dioxide interface as the surface potential. Figure 638. Subthreshold conduction in metal oxide semiconductor field effect transistor, A. Semi-log plot of drain current versus gate voltage, B. Equivalent circuit showing capacitor divider, which determines subthreshold slope. Ultimately, it is the surface potential that is responsible for modulating the barrier between source and drain, and therefore the drain current. Hence, S is a measure of the efficacy of the gate potential in modulating drain current. From EQ 666, we observe that S is improved by reducing the gate oxide thickness, which is reasonable because if the gate electrode is closer to the channel, the gate control is obviously better. The value of S is higher for heavy channel doping, which increases the depletion capacitance, or if the silicon oxide interface has many fast interface states. For a very small gate voltage, the subthreshold current is reduced to the leakage current of the source/drain junctions. This determines the off-state leakage current, and therefore the standby power dissipation in many complementary MOS, CMOS, circuits involving both N-channel and P-channel MOSFETs. It also underlines the importance of having high-quality source/drain junctions. From the subthreshold characteristics, it can be seen that if the threshold voltage of a MOSFET is too low, it cannot be turned off fully at Vg equals 0. Also, unavoidable statistical variations of threshold voltage cause drastic variations of the subthreshold leakage current. On the other hand, if threshold voltage is too high, one sacrifices drive current, which depends on the difference between the power supply voltage and threshold voltage. For these reasons, the threshold voltage of metal oxide semiconductor field effect transistors has historically been designed to be 0.7 volts. However, with the recent advent of various types of low voltage, low power portable electronics, there are new challenges in device and circuit design to optimize speed and power dissipation. Equivalent circuit for the MOSFET. When we attempt to draw an equivalent circuit of a MOSFET, we find that in addition to the intrinsic MOSFET itself, there are a variety of parasitic elements associated with it. An important addition to the gate capacitance is the so-called Miller overlap capacitance due to the overlap between the gate and the drain region, Fig 639. This capacitance is particularly problematic because it represents a feedback path between the output drain terminal and the input gate terminal. One can measure the Miller capacitance at high frequency by holding the gate at ground, Vg equals 0, so that an inversion layer is not formed in the channel. Thereby, most of the measured capacitance between gate and drain is due to the Miller capacitance, rather than the gate capacitance Ci. It is possible to minimize this capacitance by using a so-called self-aligned gate. In this process, the gate itself is used to mask the source/drain implants, thereby achieving alignment. Even in this design, however, there is still a certain amount of overlap because of the lateral straggle or spread of the implanted dopants underneath the gate, further exacerbated by the lateral diffusion which occurs during high-temperature annealing. This spread of the source/drain junctions under the gate edge determines what is called the channel length reduction, LR, Fig 640. Hence, we get the electrical or effective channel length, LEF, in terms of the physical gate length, L as Figure 639. Equivalent circuit of a metal oxide semiconductor field effect transistor, showing the passive capacitance and resistive components. The gate capacitance C is the sum of the distributed capacitances from the gate to the source end of the channel, and the drain end. In addition, we have an overlap capacitance, where the gate electrode overlaps the source/drain junctions, from the gate to source and gate to drain. Capacitance is also known as the Miller capacitance. We also have p-n junction depletion capacitances associated with the source and drain. The parasitic resistances include the source/drain series resistances, and the resistances in the substrate between the bulk contact and the source and drain. The drain current can be modeled as a gate voltage controlled constant current source. There can also be a width reduction, Z, which changes the effective width, ZEFF, from the physical width Z of the MOSFET. The width reduction results from the electrical isolation regions that are formed around all transistors, generally by locos. The locos isolation technique is discussed in section 9.3.1. Another very important parameter in the equivalent circuit is the source/drain series resistance, RSD equal, Rs plus Rd, because it degrades the drain current and transconductance. For a certain applied drain bias to the source/drain terminals, part of the applied voltage is wasted as an ohmic voltage drop across these resistances, depending on the drain current, or gate bias. Hence, the actual drain voltage applied to the intrinsic MOSFET itself is less. This causes ID to increase sublinearly with Vg. We can determine RSD, along with LR, from the overall resistance of the MOSFET in the linear region. This corresponds to the intrinsic channel impedance R chapter, plus the source drain resistance RSD. Modifying EQ 651, we get Figure 640. Determination of length reduction and source/drain series resistance in a metal oxide semiconductor field effect transistor. The overall resistance of a metal oxide semiconductor field effect transistor in the linear region is plotted as a function of channel length, for various substrate biases. The X mark data points for three different physical gate lengths L. We can measure drain voltage divided by drain current in the linear range for various metal oxide semiconductor field effect transistors having the same width, but different channel lengths, as a function of substrate bias. Varying the substrate bias changes the Vt through the body effect, and therefore the slope of the straight lines that result from plotting the overall resistance as a function of L. The lines pass through a point, having values which correspond to LR and RSD, as shown in Fig 640. MOSFET scaling and hot electron effects. Much of the progress in semiconductor integrated circuit technology can be attributed to the ability to shrink or scale the devices. Scaling down MOSFETs has a multitude of benefits. From Table 6.1, we see the benefits of scaling in terms of the improvement of packing density, speed and power dissipation. A key concept in scaling, first due to Denord at IBM, is that the various structural parameters of the MOSFET should be scaled in concert if the device is to keep functioning properly. In other words, if lateral dimensions such as the channel length and width are reduced by a factor of k, so should the vertical dimensions such as source/drain junction depths, xj, and gate insulator thickness, Table 6.1. Scaling of depletion widths is achieved indirectly by scaling up doping concentrations. However, If we simply reduce the dimensions of the device and kept the power supply voltages the same, the internal electric fields in the device would increase. For ideal scaling, power supply voltages should also be reduced to keep the internal electric fields reasonably constant from one technology generation to the next. Unfortunately, in practice, power supply voltages are not scaled hand in hand with the device dimensions, partly because of other system-related constraints. Table 6.1. Scaling rules for metal oxide semiconductor field effect transistors according to a constant factor K. The horizontal and vertical dimensions are scaled by the same factor. The voltages are also scaled to keep the internal electric fields more or less constant, and the hot carrier effects manageable. Scaling factor of surface dimensions 1/K. Scaling factor of vertical dimensions 1/K. Scaling factor of impurity concentrations K. Scaling factor of current and voltage 1/K. Scaling factor of current density K. Scaling factor of capacitance per unit area K. Scaling factor of transconductance 1. Scaling factor of circuit delay time 1/K. Scaling factor of power dissipation 1/K squared. Scaling factor of power density 1. Scaling factor of power delay product 1/K cubed. The longitudinal electric fields in the pinch-off region, and the transverse electric fields across the gate oxide, increase with MOSFET scaling. A variety of problems then arise which are generically known as hot electron effects and short channel effects, Fig 641. When an electron travels from the source to the drain along the channel, it gains kinetic energy at the expense of electrostatic potential energy in the pinch-off region, and becomes a hot electron. At the conduction band edge, the electron has potential energy only. As it gains more kinetic energy, it moves higher up in the conduction band. A few of the electrons can become energetic enough to surmount the 3.1 electron volts potential barrier between the silicon channel and the gate oxide, Fig 625. Some of these injected hot electrons can go through the gate oxide and be collected as gate current, thereby reducing the input impedance. More importantly, some of these electrons can be trapped in the gate oxide as fixed oxide charges. According to EQ 637, this increases the flat band voltage, and therefore the threshold voltage. In addition, these energetic hot carriers can rupture SiH bonds that exist at the silicon dioxide interface, creating fast interface states that degrade MOSFET parameters such as transconductance and subthreshold slope, with stress. The results of such hot carrier degradation are shown in Fig 642, where we see the increase of threshold voltage and decrease of slope, and therefore transconductance, with stress. The solution to this problem is to use what is known as a lightly doped drain, LDD. Figure 641. Short channel effects in metal oxide semiconductor field effect transistor. As metal oxide semiconductor field effect transistors are scaled down, potential problems due to short channel effects include hot carrier generation, electron-hole pair creation, in the pinch-off region, punch-through breakdown between source and drain, and thin gate oxide breakdown. Figure 6-42. Hot carrier degeneration in metal oxide semiconductor field effect transistors. The linear region transfer characteristics before and after hot carrier stress indicate an increase of voltage and decrease of transconductance, or channel mobility, due to hot electron damage. The damage can be due to hot electron injection into the gate oxide, which increases the fixed oxide charge, and increasing fast interference state densities at the oxide-silicon interface, indicated by X. As discussed in more detail in section 9.3.1, by reducing the doping concentration in the source/drain, the depletion width at the reverse biased drain channel junction is increased and the electric field is reduced. Hot carrier effects are less problematic for holes in p-channel MOSFETs than for electrons in n-channel devices for two reasons. The channel mobility of holes is approximately half that of electrons, hence, for the same electric field, there are fewer hot holes than hot electrons. Unfortunately, the lower hole mobility is also responsible for lower drive currents in p-channel than in n-channel. Also, the barrier for hole injection in the valence band between silicon and silicon dioxide is higher, 5 electron volts, than for electrons in the conduction band, 3.1 electron volts, as shown in Fig 625. Hence, while LDD is mandatory for n-channel, it is often not used for p-channel devices. One signature for hot electron effects is substrate current, Fig 643. As the electrons travel toward the drain and become hot, they can create secondary electron-hole pairs by impact ionization, Fig 641. The secondary electrons are collected at the drain, and cause the drain current in saturation to increase with drain bias at high voltages, thereby leading to a decrease of the output impedance. The secondary holes are collected at the substrate as substrate current. This current can create circuit problems such as noise or latch-up in CMOS circuits, section 9.3.1. It can also be used as a monitor for hot electron effects. As shown in Fig 643, substrate current initially increases with gate bias, for a fixed, high drain bias, goes through a peak, and then decreases. The reason for this behavior is that initially, as the gate bias increases, the drain current increases and thereby provides more primary carriers into the pinch-off region for impact ionization. Figure 643. Substrate current in a metal oxide semiconductor field effect transistor. The substrate current in n-channel metal oxide semiconductor field effect transistor due to impact-generated holes in the pinch-off region, as a function of gate bias. The substrate current initially increases with gate voltage, because of the corresponding increase of drain current. However, for even higher gate voltage, the metal oxide semiconductor field effect transistor goes from the saturation to the linear region, and the high electric fields in the pinch-off region decrease, causing less impact ionization. However, for even higher gate bias, the MOSFET goes from the saturation region into the linear region when the fixed VD drops below VD, sat equal, VG, VT. The longitudinal electric field in the pinch-off region drops, thereby reducing the impact ionization rates. Hot electron reliability studies are done under worst-case conditions of peak substrate current. These are generally done under accelerated conditions of higher than normal operating voltages so that if there are any potential problems, they show up in a reasonable time period. The degradation data is then extrapolated to the actual operating conditions. Drain-induced barrier lowering. If small channel length MOSFETs are not scaled properly, and the source/drain junctions are too deep or the channel doping is too low, there can be unintended electrostatic interactions between the source and the drain known as drain-induced barrier lowering, DIBL. This leads to punch-through leakage or breakdown between the source and the drain, and loss of gate control. The phenomenon can be understood from Fig 644, where we have schematically plotted the surface potential along the channel for a long channel device and a short device. We see that as the drain bias is increased, the conduction band edge, which reflects the electron energies, in the drain is pulled down, and the drain channel depletion width expands. For a long channel MOSFET, the drain bias does not affect the source-to-channel potential barrier, which corresponds to the built-in potential of the source channel PN junction. Hence, unless the gate bias is increased to lower this potential barrier, there is little drain current. On the other hand, for a short channel MOSFET, as the drain bias is raised and the conduction band edge in the drain is pulled down, with a concomitant increase of the drain depletion width, the source channel potential barrier is lowered due to DIBL. This can be shown numerically by a solution of the two-dimensional Poisson equation in the channel region. The physics can be captured by an equivalent circuit which shows the gate capacitance, Ci and a drain capacitance Cd are competing for control of the channel potential near the source end, Fig 633. Simplistically, the onset of DIBL is sometimes considered to correspond to the drain depletion region expanding and merging with the source depletion region, and causing punch-through breakdown between source and drain. However, it must be kept in mind that DIBL is ultimately caused by the lowering of the source junction potential barrier below the built-in potential. Hence, if we get DIBL in a MOSFET for a grounded substrate, the problem can be mitigated by applying a substrate reverse bias, because that raises the potential barrier at the source end. This works in spite of the fact that the drain depletion region interacts even more with the source depletion region under such back bias. Once the source channel barrier is lowered by DIBL, there can be significant drain leakage current, with the gate being unable to shut it off. Figure 644. Drain-induced barrier lowering in metal oxide semiconductor field effect transistors. Cross-sections and potential distribution along the channel for a long and short channel metal oxide semiconductor field effect transistor. What are the solutions to this problem? The source/drain junctions must be made sufficiently shallow, i.e., scaled properly, as the channel lengths are reduced, to prevent DIBL. Secondly, the channel doping must be made sufficiently high to prevent the drain from being able to control the source junction. This is achieved by performing what is known as an anti-punch-through implant in the channel. Sometimes, instead of such an implant throughout the channel, which can have undesirable consequences such as raising the VT or the body effect, a localized implant is done only near the source/drains. These are known as halo or pocket implants. The higher doping reduces the source/drain depletion widths and prevents their interaction. Figure 645. Short channel effect in a metal oxide semiconductor field effect transistor. Cross-sectional view of metal oxide semiconductor field effect transistor along the length showing depletion charge sharing, colored regions, between the gate, source and drain. For short channel MOSFETs, DIBL is related to the electrical modulation of the channel length in the pinch-off region, L. Since the drain current is inversely proportional to the electrical channel length, we get for small pinch-off regions, L. We assume that the fractional change in the channel length is proportional to the drain bias, where L is the channel length modulation parameter. Hence, in the saturation region, the expression for the drain current becomes this leads to a slope in the output characteristics, or a lowering of the output impedance, Fig 632. Short channel effect and narrow width effect. If we plot the threshold voltage as a function of channel length in metal oxide semiconductor field effect transistors, we find that threshold voltage decreases with length for very small geometries. This effect is called the short channel effect, SCE, and is somewhat similar to drain-induced barrier lowering. The mechanism is due to something called charge sharing between the source/drain and the gate, Fig 645. From the equation for the threshold voltage, 638, we notice that one of the terms is the depletion charge under the gate. The equipotential lines in Fig 645 designating the depletion regions curve around the contours of the source/drain junctions. Keeping in mind that the electric field lines are perpendicular to the equipotential contours, we see that the depletion charges that are physically underneath the gate in the approximately triangular regions near the source/drains have their field lines terminate not on the gate, but instead on the source/drains. Hence, electrically these depletion charges are shared with the source and drain regions and should not be counted in the threshold voltage expression, EQ. 638. We can deal with this effect by replacing the original QD in the rectangular region underneath the gate by a lower QD in the trapezoidal region in Fig 645. Clearly, for a long channel device, the triangular depletion charge regions near the source and drain are a very small fraction of the total depletion charge underneath the gate. However, as the channel lengths are reduced, the shared charge becomes a larger fraction of the total, and this results in a threshold voltage roll-off as a function of L, Fig 646. This is important because it is hard to control the channel lengths precisely in manufacturing. The channel length variations then lead to problems with threshold voltage control. In the last several years, another effect has been observed in N-channel metal oxide semiconductor field effect transistors with decreasing L. The threshold voltage initially goes up before it goes down due to the short channel effect. This phenomenon has been dubbed the reverse short channel effect, RSCE, and is due to interactions between silicon point defects that are created during the source/drain implant and the boron doping in the channel, causing the boron to pile up near the source and drains, and thus raise the threshold voltage. Another related effect in metal oxide semiconductor field effect transistors is the narrow width effect, where the threshold voltage goes up as the channel width Z is reduced for very narrow devices, Fig 646. This can be understood from Fig 647, where some of the depletion charges under the Locos isolation regions have field lines electrically terminating on the gate. Figure 646. Roll-off of voltage with decreasing channel length, and increase of voltage with decreasing width. Unlike the SCE, where the effective depletion charge is reduced due to charge sharing with the source/drain, here the depletion charge belonging to the gate is increased. The effect is not important for very wide devices, but becomes quite important as the widths are reduced below 1 micrometer. Figure 647. Narrow width effect in a metal oxide semiconductor field effect transistor. Cross-sectional view of metal oxide semiconductor field effect transistor along the width, showing additional depletion charge, colored regions, underneath the field or the isolation regions. Gate-induced drain leakage. If we examine the sub-threshold characteristics shown in Fig 638, we find that as the gate voltage is reduced below threshold voltage, the sub-threshold current drops and then bottoms out at a level determined by the source/drain diode leakage. However, for even more negative gate biases we find that the off-state leakage current actually goes up as we try to turn off the metal oxide semiconductor field effect transistor more for high drain voltage. This is known as gate-induced drain leakage, GIDL. The same effect is seen at a fixed gate bias of near zero, for increasing drain bias. The reason for GIDL can be understood from Fig 648, where we show the band diagram as a function of depth in the region where the gate overlaps the drain junction. As the gate is made more negative, or alternatively, for a fixed gate bias, the drain is made more positive, a depletion region forms in the N-type drain. Since the drain doping is high, the depletion widths tend to be narrow. If the band bending is more than the band gap, e.g. across a narrow depletion region, the conditions are conducive to band-to-band tunneling in this region, thereby creating electron-hole pairs. The electrons then go to the drain as gate-induced drain leakage. It must be emphasized that this tunneling is not through the gate oxide, section 6.4.7, but entirely in the SI drain region. For gate-induced drain leakage to occur, the drain doping level should be moderate, 1018 cm, 3. If it is much lower than this, the depletion widths and tunneling barriers are too wide. On the other hand, if the doping in the drain is very high, most of the voltage drops in the gate oxide, and the band bending in the SI drain region drops below the value, e.g. Gate-induced drain leakage is an important factor in limiting the off-state leakage current in state-of-the-art metal oxide semiconductor field effect transistors. Figure 648. Gate-induced drain leakage in metal oxide semiconductor field effect transistor. The band diagram for the location shown in color is plotted as a function of depth in the gate-drain overlap region, indicating band-to-band tunneling and creation of electron-hole pairs in the drain region in the silicon substrate. Metal gate high K. As described above, the silicon metal oxide semiconductor field effect transistor with thermally grown silicon dioxide gate dielectric with its high-quality interface, and heavily doped polysilicon gate electrode has been the workhorse in this field for decades. However, due to the problems of tunneling leakage currents in ultra-thin silicon dioxide gate dielectrics, in recent years there has been a shift to high-K gate dielectrics such as hafnium dioxide, which can be made physically thicker without sacrificing gate capacitance, Ci = pi/d. Generally, higher dielectric constant materials have lower band gaps than silicon dioxide. Hence, the band offsets in the conduction and valence bands may also be lower between these high-K gate dielectrics and silicon. Thus, while the gate dielectric tunnel barriers may be wider, the heights of the barriers may be lower than for silicon dioxide on silicon. Another complication is that the electrical interfaces between the high-K dielectrics and silicon are worse than between thermally grown silicon dioxide and silicon, leading to degraded channel mobilities. Hence, it is common to grow a thin interfacial silicon dioxide layer between the high-K dielectric and the silicon channel in order to recover the high effective channel mobilities. A common technique for deposition of such high-K dielectrics is atomic layer deposition, ALD. Atomic layer deposition is a type of CVD where one alternately cycles in a self-limiting fashion between two types of gas precursors that are needed to grow the material. For instance, to grow hafnia, HFO2, in one cycle we saturate the Si surface with a monolayer of a hafnium-containing precursor, after which the precursor will not adsorb under the selected conditions of substrate temperature and gas pressure. We flush out the HF precursor, and flow in the oxygen-containing precursor, water, which will complete the growth of a monolayer of hafnium dioxide. Then, we go to the next cycle by flushing out the water, and flowing in the hafnium precursor. Thus, we achieve digital control over the layer thicknesses where the growth depends on the number of the growth cycles rather than the growth time, as in conventional CVD. Such control is particularly important for ultra-thin gate dielectrics. In addition to a shift from silicon dioxide to high-K dielectrics, there has been a shift from doped polysilicon gates to metal gates with appropriate work functions. As seen in EQ 638, this can be used to engineer the flat band voltage, and thus the threshold voltage of a MOSFET. This is sometimes referred to as gate work function engineering. It is interesting that in some ways, things have come full circle. The first metal oxide semiconductor field effect transistors were made with aluminum gates, which were supplanted by refractory polysilicon gates which could be patterned to form masks for the self-aligned source-drain implants and high-temperature anneals. We have now gone back to metal gates, using refractory materials. In some MOSFET fabrication flows, in order to be able to integrate the high-K dielectrics which cannot survive the high process temperatures of source-drain anneals, the source drains are formed first with a dummy, sacrificial gate electrode. This gate electrode is then etched off, the high-K dielectric deposited, and the metal gate formed. Such processes have been dubbed the gate last process. In addition to engineering the gate stack, one must carefully design the source/drain junctions, the channel doping profile, and the contact metallurgy on the various electrodes to reduce resistance. Those details are discussed in section 9.3.1. Enhanced channel mobility materials and strained SiFETs. The HEMT described in section 6.3.2 is capable of high-frequency operation and high drive currents because of the high carrier mobilities in the 3-5 channel. However, the device tends to suffer from high gate leakage currents and, therefore, low input impedance because of the use of Schottky gates which tend to be leakier than metal oxide semiconductor gates. Unfortunately, high-quality native thermal oxides such as silicon dioxide on silicon cannot be grown on 3-5 materials. With the advent of deposited high-K gate dielectrics on silicon MOSFETs, there was a similar move toward depositing high-K gate dielectrics on high electron mobility compound semiconductors such as indium gallium arsenide, to make 3,5N metal oxide semiconductor field effect transistors with better performance than silicon. Most 3-5 column semiconductors unfortunately have low hole mobilities, hence, for P metal oxide semiconductor field effect transistors, germanium is a better choice since it has a hole mobility 4 times that of silicon. A more careful examination of the problem, however, reveals that the movement to high mobility channels may not always be justified. The drive current in a MOSFET can be somewhat simplistically considered to be proportional to the product of carrier density in the channel times the carrier velocity. The carrier velocity in these high mobility channel materials is expected to be higher than in Si because it is inversely proportional to the lower conductivity effective mass EQ. 336. Unfortunately, the carrier density, which depends on the density of states in the channel, is directly proportional to the density of states effective mass in a 2D system such as an inversion layer EQ. IV10b, in Appendix 4. Hence, there is a cancellation of the effective mass terms in the drive current expression. This is known as the density of states bottleneck in these high mobility channels. In addition, the highest doping densities in the source drains of such high channel mobility materials are sometimes not as high as in silicon, leading to higher source drain access resistance. Finally, we find that many semiconductors with low effective mass have low band gaps. Simplistically, this is because low effective masses are associated with high band curvature, which generally implies wider bands due to larger overlap of wave functions, and lower band gaps. The low band gaps cause high off-state leakage currents in metal oxide semiconductor field effect transistors, which is particularly problematic for low-power logic circuits. Nevertheless, a more detailed analysis shows that under some circumstances, these high-channel mobility metal oxide semiconductor field effect transistors can indeed outperform Si. Another approach to improving carrier mobilities is to introduce mechanical strain in the semiconductors. For instance, in Si, if uniaxial tensile strain is introduced in one direction, or biaxial strain in two directions, in order to break the cubic symmetry of the unit cell, it breaks the six-fold degeneracy of the conduction band minima in the 100 directions near the X point, Fig 310a. In bulk silicon, for transport in any of the 100 directions, we get a contribution from two ellipsoidal valleys with high milliliter, and four valleys with low mount, as described in example 3.6. Under biaxial tensile strain, there is a contraction of the planes in the third direction, and the two valleys in this direction are lowered in energy and are preferentially occupied. For transport in the plane of tensile strain, both these valleys have the lower transverse effective mass, mount, leading to an enhancement of the electron mobility, Fig 649. There is also reduced intervalley scattering, leading to a higher scattering mean free time and higher mobility EQ. 340a. Similar enhancements in hole mobility are achievable with compressive strain in silicon. Figure 649. Energy ellipsoids in silicon shown with respect to metal oxide semiconductor field effect transistor made on silicon. Confinement by the inversion layer potential in the vertical direction lowers the two valleys in the z direction, tensile strain lowers them even more, reducing scattering between the valleys. Also, since these ellipsoids have the lower m, in the transport direction from source to drain, there is enhancement of mobility and drain current. These effects can be exploited in strained Si channels to enhance MOSFET drive currents, although there are additional complications due to carrier confinement in the inversion layers. One way to introduce biaxial tensile strain in silicon is to epitaxially grow it on relaxed, larger lattice constant silicon germanide buffer layers grown on a substrate see Fig 114. Alternatively, uniaxial tensile strain can be introduced by judicious deposition of stressor layers of silicon nitride on the silicon metal oxide semiconductor field effect transistors. Similarly, process-induced compressive strain is created in silicon MOSFETs by etching trenches in the source drain regions and refilling them with larger lattice constant silicon germanide layers. SWA MOSFETs and FinFETs. In the previous section, we discussed some of the problems, such as leakage due to punch-through, in short-channel metal oxide semiconductor field effect transistors in bulk silicon. It is also important to recognize that most of the current flow in the MOSFET is restricted to a thin layer comparable to the inversion layer thickness, 10 nanometers, near the surface, and most of the bulk silicon substrate acts merely as mechanical support for the MOSFET, and has no electrical function whatsoever. These considerations led to the development of the silicon on-insulator MOSFET, SWA MOSFET, shown in Fig 650a, made in a thin, 10 to 100 nanometers, silicon single crystal film on an insulating buried oxide, box, layer, 100 nanometers thick, on a bulk silicon substrate. Since silicon dioxide can easily be grown on silicon substrates, it serves as an attractive insulator for subsequent growth of thin film silicon. Since polycrystalline Si can be deposited directly over silicon dioxide, devices can be made in thin polysilicon films. However, To avoid grain boundaries and other defects typical of polycrystalline material, a variety of techniques have been developed to grow single crystal silicon on oxide. Figure 650. A. Silicon on insulator. Both N-channel and P-channel enhancement transistors are made in islands of silicon film on the insulating substrate. These devices can be interconnected for complementary metal oxide semiconductor applications. B. FIN-FET and comparison to planar metal oxide semiconductor field effect transistor. C. Scanning electron micrograph of multiple FIN-22 nanometer 3-gate field effect transistors connected Indiana parallel to increase the effective width. For example, the oxide layer can be formed beneath the surface of a silicon wafer by high-dose oxygen implantation. The thin silicon layer remaining on the surface above the implanted oxide is usually about 0.1 micrometer thick, and can be used as the thin film for CMOS or other device fabrication. This process is called separation by implantation of oxygen, SIMOX. In some cases a thicker silicon film is grown epitaxially on the SIMOX wafer, using the thin silicon crystalline layer over the oxide as a seed for the epitaxy. Another approach for making SWA is to place two oxidized silicon wafers face to face, and thermally bond the oxide layers by high-temperature annealing in a furnace. One of the wafers is then chemically etched back almost completely, leaving a fraction of a micron of single crystal silicon material on top of the silicon dioxide. This approach is known as bond and etch back SWA, BESOI. Since it is challenging to etch off about 600 micrometers of silicon and stop controllably so as to leave about a micron of silicon, an initial P+ implanted layer is often used to act as an etch stop near the end of the chemical etch. The chemical recipe that is used for etching silicon has a much lower etch rate in a P+ layer than in lightly doped silicon. Another approach known as smart cut is a modification of BSWA using very high dose H implantation into one of the oxidized silicon wafers, such that the peak of the H profile is about a micron below the silicon surface. During the high temperature annealing step, the H atoms coalesce to form tiny H bubbles which cause a thin layer of Si to cleave off from the implanted wafer, leaving the Si layer bonded to the oxidized silicon surface. This way, we do not have to chemically etch off one Si wafer for every BSWA wafer. If properly done, the cleaved-off Si wafer has a fairly smooth surface and can be reused. Another suitable substrate for such devices is silicon on sapphire, SOS. Epitaxial silicon films can be grown on crystalline sapphire, aluminum oxide, substrates by chemical vapor deposition, for example, the pyrolysis of silane, with typical film thickness of about 1 ohm. This is sometimes referred to as SWA-SOS, a term which can elicit a laugh in an otherwise serious discussion. The thin SWA film can be patterned by standard photolithographic techniques into islands for each transistor, making electrical isolation of adjacent MOSFETs simpler than for bulk silicon. Implantation of P+ and N+ areas into these islands for source and drain regions result in the MOS devices. Since the film is so thin, the source and drain regions can be made to extend entirely through the film to the insulating substrate. As a result, the junction capacitance is reduced to the very small capacitance associated with the sidewalls between the source/drain and the channel region. In addition, since interconnections between devices pass over the insulating substrate, the usual interconnection silicon substrate capacitance is reduced, along with the possibility of parasitic-induced channels in the field between devices. These capacitance reductions improve considerably the high-frequency operation and power consumption of circuits using such devices. The electrostatic behavior of the SWA MOSFET in saturation is improved, because the thinness of the channel layer means the gate exerts better control of the channel potential than the drain, compared to a bulk MOSFET. Therefore problems such as DIBL are reduced. Since the leakage paths in the bulk silicon far from gate control are blocked by the box layer, the off-state leakage is lower in SWA MOSFETs, and the channel lengths can be controlled more aggressively. In fully depleted extremely thin channel, 10 nanometers, SWA MOSFETs, where the channel depletion layer can extend throughout the SWA film under typical gate biases, it is possible to leave the channel undoped and still avoid punch-through, and achieve the required threshold voltage by choosing the gate work function appropriately. Undoped channels have the advantage of having high carrier mobility due to reduced ionized impurity scattering, and less VT variations. In a scaled bulk MOSFET, the total number of dopants in the channel, which is equal to the doping density times channel volume, equal width * length * depletion width, is quite small and susceptible to statistical dopant number fluctuations, leading to threshold voltage variability. An undoped channel SWA MOSFET avoids this problem. As discussed, the top gate in an SWA MOSFET improves control of the channel potential compared to bulk devices and leads to better scalability. The electrostatic control can be improved further if multiple gates can be incorporated to control the channel potential. An elegant way to achieve this is to etch thin fins of height h and width w in the SWA film, deposit high K gate dielectrics on the fins, pattern gates over them, and use the gate as a self-aligned mask to implant source drains in the fin, adjacent to the gate, Fig 650b. Notice that this is a non-planar 3D geometry of the MOSFET, where the channel is mostly on the two vertical sidewalls of the fins. The effective width of a so-called fin FET is 2h plus w, times the number of parallel fins. The two self-aligned gates on the sidewalls improve electrostatic control even more than a top-gated SWA MOSFET. Variations of the fin FET are known as multiple gate FETs, MUGFETs, or tri-gate FETs. The SWA approach does not suffer from the latch-up problem of bulk CMOS discussed in Chapter 9 because there is no PNP thyristor from the power supply to ground. For circuits requiring high speeds, low standby power due to the elimination of junction leakage to the substrate, and alpha particle radiation, from cosmic rays and radioactive impurities, tolerance due to the elimination of the silicon substrate, the extra expense of preparing SWA substrates is compensated by increased performance. Summary: 6.13 Terminal active devices capable of power gain are key to the switching and amplification of electronic signals. The input impedance is, desirably, high for voltage-controlled FETs and low for current-controlled bipolar junction transistors. The power gain of the AC signal comes from the DC power supply. It is also desirable to have a high output impedance and a linear dependence of output current with respect to input voltage, or current. 6.2 Field effect devices such as the GFETs, or MESFETs and HEMTs, use a reverse-biased PN junction, or Schottky diode, as a gate to control the undepleted part of a channel and thereby modulate the current flow between a source, S, of carriers and a drain, D, of carriers. 6.3 The MOSFET uses an oxide-isolated gate, MOS capacitor, that has a very high input impedance to modulate the barrier between S and D and to change the conductivity of the channel. 6.4 An enhancement mode NMOS-FET has a p-type channel between the N+ source and the drain regions. At the flat band conditions, VFB, there is no band bending as a function of depth in the channel. A gate bias more negative than VFB causes exponentially more holes to be accumulated near the surface with band bending. 6.5 More positive gate voltages initially repel the majority carrier holes and create a depletion region. Then, above the threshold voltage, VT, they attract minority carrier electrons near the surface and invert the surface, thereby forming a conductive channel between source and drain. P-metal oxide semiconductor field effect transistors have the opposite polarities. 6.6 The VT can be increased by increasing the channel doping and the gate oxide thickness, lower CI. It is also affected by VFB, which depends on the gate work function and oxide charges, and increases with substrate reverse bias, body effect, as well. 6.7 The overall MOS capacitance is the series combination of a fixed gate capacitance Ci and the voltage-dependent semiconductor capacitance in the channel. The inversion charge per unit area is approximately Ci, Vg, Vt. 6.8 For long-channel MOSFETs, initially ID increases linearly with Vd, and then it saturates once the inversion channel is pinched off near the drain end. 6.9 There is a quadratic dependence of ID on Vg for long channel MOSFETs. For short channel devices that operate in the velocity saturated region or source injection regime, the dependence of ID on Vg is approximately linear. 6.10 For short L, IDSAT often increases slightly with Vd due to various short channel effects, leading to a decrease of output impedance. Short channel effects include drain-induced barrier lowering, DIBL, and charge sharing, which leads to Vt roll-off with L. 6.11 There is some conduction below threshold voltage, characterized by a sub-threshold slope, that is a measure of the effectiveness of the MOSFET as a switch. 6.12 Conduction above threshold voltage in the channel inversion region reflects an effective channel mobility lower than that in bulk due to surface roughness scattering, and increasingly so at higher Vg. 6.13 In highly scaled metal oxide semiconductor field effect transistors, there can be gate tunneling leakage currents, mitigated by high K dielectrics, and hot electron, and, to a lesser extent, hole effects, mitigated by lower power supply voltages and lightly doped drains, LDDs. The resulting high SD parasitic series resistance is minimized by self-aligned silicides, salicide, described in Chapter 9.